over, because these lectures are easier and you just have to understand the concept. And then it's just memorization, okay? So if you guys want, you can always use those. Okay, so let's start. So in this lecture, okay, so the way I'm going to do this is first I'm going to give you the lecture, tell you most important things about the lecture while going through it. And then I will summarize the lecture in like 2 or 3 minutes. And then if you have any questions after that, you can ask. If you have any questions during that, please write it in the chat, and inshallah, I'll try to answer them, okay? So this lesson, Principles of Epidemiology, basically, there's 2 important concepts. One is relative risk and the other is odds ratio, okay? So for both of these methods, they're used by epidemiologists to compare the probability. Let's see if I can change this to a pointer. Okay, so basically, they want to measure the risk of disease in 2 different groups. So basically, when people carry out studies, they want to check which group is more likely to getting a disease. They use either relative risk or odds ratio, okay? So relative risk uses proportions. So what are proportions? Proportion is basically a fraction. What is important in a fraction? The numerator is always part of the denominator. It's not something outside the main, the total group, okay? So that's basically what proportion is. So now relative risk, I've never done a Zoom teaching session before. Usually I use a blackboard or whiteboard. So I put these out mid slides that could be easier to understand. So basically, let's go relative risk again. Okay, so relative risk describes the likelihood of developing a disease in an exposed group compared to a non-exposed group, okay? So basically, it takes the risk of disease in one group and compares it with one which is in non-exposed, okay? So to give you the example of this is a cohort study. In this type of study, what we do is first we find one variable that we want to measure. Over here it is person who is taking a pill, okay? So then we see if this people who take pill and people who do not take pill, do these people get a certain outcome? Over here it's a heart attack. It's just a random example. So the idea is that you go forward in time in this study design, and this is where we use relative risk. How do we calculate relative risk? Basically, we take the proportion of the people who were exposed to a certain condition. Over here, it's taking the pill, okay? So we take that as A, and then we go A over A plus B, which is the total number of people who were exposed. And then we divide that by the number of non-exposed over the total number of people who were non-exposed. Does this make sense so far? Okay, could I repeat? So basically, a cohort study is a type of study in which we have a certain parameter. We expose the population, our study population, to something, okay? So in this case, we have exposed them to taking a pill. C is people with disease, but not exposed. Yeah, so basically, we want to measure the risk of someone developing a disease. The disease over here is heart attack, okay? So we want to see how many people, the proportion of people who developed a disease who were exposed to this. So that's proportion of people who were exposed. So this is the total. A plus B is the total people who were exposed. And out of that, we're taking the proportion of people who developed a disease. And then over here, we're taking the total, which is non-exposed. And then we're taking the number of people who developed a disease or are non-exposed. So when we divide both of these ratios, we get a relative risk. Okay, so basically, relative risk describes the likelihood of developing a disease in an exposed group compared to that of a non-exposed group. Okay, is the ratio risk of probability of disease among the exposed to the risk of disease among the non-exposed. So basically, P exposed is the proportion of people who were exposed. So proportion who got the disease over total people who were exposed, and then disease unexposed and total people who were unexposed. Okay. So over here, it's the same thing exactly. what else over here? Okay, so this is an example that makes it a lot easier to understand. So basically, in a study of 1,000 people, investigators observed those who were bitten by a flea and developed the plague. So people who, the disease over here is developing the plague, and people exposed are people who got bitten by a flea. So when they were trying to find the relative risk, they basically took exposed over total, then non-exposed over total. So it was basically 400 over 600 divided by 100 over 400. Okay, and once they got this relative risk, this meant that this group, the exposed group, is 2.7 times more likely to develop a plague than the group which was not exposed. Does that make sense? We're trying to figure out if this particular thing, being bitten by a flea, is actually causing the disease or not. Or, okay, so this is not causation. This is basically how much more likely are people who are bitten by fleas to develop this disease. Does this clarify something? Okay, great. So basically, relative risk can be of three types. You can either get one, which means that there is no association between exposure and disease, which basically means that the people who are bitten by fleas can get the disease, as can the people who are not bitten by fleas. So there's no relative risk of one group having a higher probability of developing a disease. Does that make sense? Something is greater than one, that means there's increased risk of developing. If something is less than one, then that means there's a decreased risk. Usually they ask this question, what does that mean? It usually means you have a protective effect, like in the example of vaccinations. So if someone is exposed to vaccinations, the chances of them getting a disease is less likely. So for example, if someone was to do a cohort study on the new COVID vaccine, which is being released nowadays, so what they will do is people who are exposed to vaccine, people who are not exposed to vaccine, and then they see, do they get COVID or do they not get COVID? And then since they're going to be following up over time, they will calculate the relative risk. Now, if the relative risk is less than one, they'll be like, oh, okay, it has a protective effect. So it is helping people. Or at least we think it's helping people. Make sense? Okay, great. Now let's go to odds ratio. So odds ratio is somewhat a bit tricky to understand, because first we have to understand what odds are. So odds can be defined as if PA is the probability of an event that is going to occur, then the odds of this event, the odds in favor of this event to occur is going to be P divided by 1 minus P. That's it, okay? And then 2, 1, we just write it because we want to know the odds of something developing relative to 1, okay? So to give you an example, okay, one more thing over here. So how is this different from a proportion? In proportion, we had a numerator, which was part of the denominator, right? Over here, we have a numerator, which is completely different from the denominator, but it's part of the same subset. Does that make sense? We didn't move on to odds ratio yet. We're just talking about odds, okay? So let me give you this example. So for example, the probability of something occurring is half, okay? Now, if you want to know what are the odds in favor of this event A happening, you will go like P, which is the probability of occurring, whereas divided by 1 minus P, which is going to be half divided by 1 minus half. And this is going to be the odd of this happening relative to 1, okay? So since 1 to 1 is equal, this row event A is equally likely to occur. Over here, they give you another example where they go 2 over 3 is the probability, and then you go 1 minus 2 over 3, which is 1 over 3. And that's equal to 1. So odds basically means how do I explain this? So it's another fancy way of comparing how likely an event is to occur, okay? But we're comparing it with the chances of it not occurring, So if something is going to occur versus the chances of it not occurring, when we combine both of these, we call it odds. What are the odds of this specific event occurring to its odds of not occurring? Does that make sense? Okay, so basically we're taking one event and we're comparing it with each other, okay? So over here, for example, if we go forward, over here, this is another example. So the probability of having TB is this, okay? Now calculate the odds of a randomly selected person having TB, okay? So we know that the probability of someone having TB is this. Now, once we go P over 1 minus P, which is basically P over 1 minus P, have the probability of having TB versus the probability of, not versus, divided by, the probability of not having TB, we say that the odds are 0.00009302121. Make sense? Okay, so basically this was how do we calculate odds, okay? This is another example where it shows you that if the total probability of an event occurring is 1, basically if P is the probability that an event occurs, 1 minus P, we can take it as Q and we can use that as a denominator. So then the odds in favor of the event occurring are 1 over 1 minus P, which is P divided by Q. Then we say that the odds of P divided by Q is, the odds are P divided by Q to 1. So to 1, we just add because we want to compare what's the chances of an event happening to not happening, you know? So we always use 1 as a relative. Yes, we always use 1 because we want to be able to make sense out of it. So for example, if you tell someone the odds of this event happening are like, 2.3, we have to use a number of comparison because it's always relative to the odds of it not happening. So we always say it's 2-1, Yes, no, these. Okay, so basically we use these odds ratios and relative risk in studies where we want to tell the people who are reading our study, how significant our data is or what does our data mean. So this is why we're like comparing it to 1 to be able to make them understand how it goes. Okay. Conversely, if the odds are in favor of the event. Okay, yeah, this is what I was trying to tell you. So if the odds of something are A to B, which means that A is something like P over here, and then to B is something like Q over here. So A and B are like this, then the probability that the event occurs is going to be A over A plus B. To make this a bit clearer, we go back to this. So basically, in this example, if we see the number of people who have heart attacks is 3, and then the people who don't have heart attacks is going to be 7. So the probability is going to be 3 out of 10. The odds are going to be 3 over 7. Does this clarify things? Okay, so basically you want to calculate the probability of a person having heart attacks. So what do? You write 3 because this is the number of people who have heart attacks, and then you divide it by the total number of people, which is 10. So probability, the numerator is always part of the denominator, okay? It includes the denominator. The numerator, yeah, is part of the denominator. That makes sense. If we're trying to calculate the odds of someone developing heart attacks to the odds of someone not developing heart attacks, we would go 3 over 7 because the odds of someone developing heart attacks is 3, and then the rest of it, 1 minus 3 is 7. So 3 over 7 is the odds. Probability is 3 over 10. Make sense? Okay, great. So if we go over here, what it's saying is if we have A over B, the odds of something happening are A to B, then the probability of that event happening is going to be A plus over A plus B. So if the odds are 2 to 1, then the probability is going to be 2 plus 2 plus 1. 2 over 2 plus 1. Make sense? Which is basically 2 over 3. Because they're adding the numerator and whatever was left from the denominator. Okay, alhamdulillah. Now this is a typical example that shows up in your exams. Okay, it's been like repeated many times. So in an experiment, 3 coins are tossed. Okay, and then they ask you, what are the odds in favor of getting exactly one tail? So what do? Remember probability in high school? You write down all the possibilities that can happen. So it could be TTH, TH, THT, T. There are 8 possibilities, okay? These are them. I am not going to waste time trying to think of them, okay? So basically you list all the possibilities, okay? Then they ask you odds in favor of getting exactly one tail. So what will be the odds of getting exactly one tail? So we look at how many options we have, right, of getting one tail only. So we have 1, 2, and there should be 3. Yeah, 3. So 1, 2, and 3. These are the chances of us getting 1t exactly, okay? And then since we're measuring, or we're trying to calculate the odds in favor of this, so we have to calculate the odds against this, which is going to be 8 minus 3, which is 5. So once we write this down, it's going to be 3 over 1 minus 3, which is 3 over 5. Or we can write it down as 3 ratio 5. Just memorize this example. Well, they may give you more or less possibilities, but usually this is an example that recurs. And you have to be smart about it. You can't just memorize it because it could be 5 ratio 3 as well, you know. So the odds of this are 3 to 5, okay? So the odds against getting exactly 2 heads. Now they're asking you a trick question. They want to know the odds against getting exactly 2 heads. What does that mean? It means basically they want you to figure out how many people can get anything other than 2 heads. Yes, not getting 2 heads. So you get either 3 heads or 1 head. So 1, 2, 3, 4, and 5. I don't know what you have, you know, all T's. So there's 5 possibilities. So 5 successes. This is what they used. So there are 5 successes. So you get 5, and then 1 divided by 1 minus 5, which is going to be 3. So the odds against getting exactly 2 heads are going to be 5 ratio 3. Make sense? They asked about the odds against getting exactly 2 heads. So basically we are calculating 1 minus 2 heads. You know, that's the way we're going for this. We want to find out the successes. Make sense? Okay. Okay. Okay, now we're moving on to the odds ratio, okay? So this was only odds. And like usually there's a typical question about odds, which is going to be something similar to this. If you look at the past exams, it like really gives you a good idea of what you're expected to memorize versus what you're supposed to understand, you know? Okay, so now let's talk about odds ratio. So odds ratio we use in a type of study known as case control study, okay? Now what's special about a case control study? It's a study design which is used for rare diseases, okay? So in this type of study design, we want to find out if there, how do I explain this? Okay, so let's just go with the picture. So in this study design, you start with the outcome, okay? So this means that if you have a rare disease, you look at a group of people who have developed this disease, and then you take a similar group of people who have not developed this disease, okay? And then you go back in time, and then you see if they were exposed to something that made it more likely for them to develop this. or which cause any difference in the outcomes. Does that make sense? So basically in a cohort study, we're going forward in time and we have exposure and non-exposure, okay? And we are checking for the outcome, checking for the disease. In this over here, it's the opposite because we know some of the people who got diseased and we know people who did not get diseased, and we're trying to check for exposure, if this certain exposure led to them developing a disease or not. Is it clear now? Nida? Okay. So for this, we use odds ratio. So wait, let's go back because I don't want to confuse you guys. So if you look over here, it is defined as the odds of a certain disease among exposed individuals divided by the odds of the same disease among the unexposed individuals, okay? OR is always stated in terms of some reference category, compares the odds of outcome for an exposed group to the odds of outcome for an unexposed group, okay? Yeah, okay, so this line is kind of like the key of all of this. So odds ratio is defined as the odds of disease among the exposed divided by the odds of the same disease among the unexposed. So we're looking at disease over here, okay? So basically, when we have this type of case control study, the disease groups are known as cases, and whoever is non-disease is known as the control, okay? So what we do over here is basically, so what we do over here is basically we take the people who were exposed and developed a disease, and then we compare them with those who developed a disease and were not exposed, okay? So this is the odds. So if this is the total, A plus C is the total, we're not going for A over A plus C. Instead, we're going for A divided by C because we want to know the odds in favor of developing a disease if they are exposed to it. Does that make sense? Okay, so we take the odds for this, and then we take the odds for this, and then we divide the two. Okay. Now, the key difference between this one and this one earlier, relative risk, was that over here we are going horizontally, okay, and we're going for the total because we have the exposure earlier. So we know the number of people who are exposed, the total number of people who are exposed. So we can go with this perfectly, you know. But over here, since we do not know the exposure earlier, we can't go horizontally, so we have to go vertically. Okay. Now this is a really, really simplified explanation of why we're going vertically. But I don't want to get into the details of this because it's just confusing. You just need to remember that if we are going back in time, we don't know the exposure, so we're calculating based on the people who develop disease because we do know. Wait, how is that any different? Any different? So basically, in cohort studies, we are going forward in time. We already know the people who are exposed and the people who are not exposed, and we want to check for outcome. So we are using A over A plus B and C over C plus D. Okay. In case control study, we don't know who was exposed earlier. We're going back in time. We only know who has the outcome or who has the disease. So we are comparing between diseased and non-diseased. Makes sense now? Okay. So that's the first difference, right? So anything that we're going back in time, we're going to use what? So it's the same numbers, right? Could you please elaborate what that means? Yeah, so whenever we're going back in time, we're going to use odds ratio because we have to compare between people who are diseased and people who are not diseased. Whenever we're going forward in time, we already know the exposure, so that's what we compare groups against. Same thing, but flipped. Relative risk is cohort study, yes. Relative risk is for cohort studies because it goes forward in time. Case controls, yes. So, yeah. Okay, so I have a question now for you guys. If it's a if it's a clinical trial, what do we go for? Do we go for relative risk or do we go for odds ratio? Just let me confirm, because I don't want to give you wrong information. Yeah, basically, we go for relative risk because we're going forward in time. Why not odds ratio? Are done on the same population spaced apart in time, would the relative risk and odds ratio be equal? I'll answer your question in bits. This question, let's hold on for a bit, okay? So basically over here, we're going for disease overexposure over 1 minus disease overexposure, okay? Which was basically this, okay? Now, if the odds ratio is 1, then there is no association because one odds is not favored by the other. If odds ratio is greater than 1, that means that there is a favorable probability or more odds of this thing happening. If it's less than 1, that means that it is a protected effect or it has negative relation. Okay, the relative risk and OR are different measures that may be used to explain the same phenomena. Compare the probability of risk between two groups of disease. Okay, although relative risk seems more intuitive because it's using probabilities, it makes more sense, right? And are easier to interpret. This is why we use relative risk whenever we can. This is now here odds ratio because relative risk is easier to interpret and more intuitive. But we use odds ratio because it gives us it has better statistical properties, which means that once it's used in other tests, it generally proves to be more statistically powerful. But don't get into this. But basically, what they mean is that if you use odds ratio in medical literature, you are more likely to get a favorable result, or not favorable. Let's put it more accurate result. So you just need to know that odds ratio has better statistical properties, especially when you're using something known as the regression analysis. If the cohort study and case are done on the same population spaced apart in time, would the relative risk and odds ratio be equal? Okay, so the odds ratio and relative risk would not be equal. They can be similar if the population size is really small, and we'll get to this in a bit. So in odds ratio, we're calculating the risk of a disease occurring, the risk of it not happening, while we're calculating the risk of a disease occurring upon exposure. The disease site no exposure. What? Calculating the risk of a disease occurring, disease not happening. Yeah, okay, this is correct. While in relative risk, we're calculating the risk of a disease occurring upon exposure. The disease, yes, exactly. Yes, you're right. Okay, so now remember how I just said if the group we're interested in is really small, then relative risk can be equal to odds ratio. So this is basically the working out of this. So if you have relative risk and that is P1 over P2, and then we want to calculate the odds ratio is going to be P over 1 minus P1 divided by P2 over 1 minus P2. And then once we rearrange them, we get P1 over P2, which they substituted here as this, they substituted here as RR because it was over here, okay? And then they compare this 1 minus P2 divided by 1 minus P1. Now they're saying if P1 and P2 are very small, then odds ratio is equal to relative risk. What do they mean? They mean if P1, let's say P2 is 0.00001, and it's the same thing for P1, it's 0.00001. So once we divide both of these, we'll get a number which is relatively similar to each other. So it will be almost the same number divided by the same number, which is going to be 1. So anything multiplied by 1 is relative risk. Does that make sense? I usually use a whiteboard to explain this, but yeah, exactly. But like on the laptop, it's really hard to write this down. Does this make sense to all of you, or do I have to show you the working? Do you want me to show you the working? So basically, it just means that if you have something, a really small number on both the numerator and the denominator, the final number will be equal to each other, which basically means that it will be equal to 1. So this is why we said that odds ratio can be equal to, can be similar to, okay? Not equal exactly, it's similar to relative risk. And this is why we can use it in case control studies, because in case control studies, why are we starting with the outcome? Because usually the disease is really rare. So you can't really expose people to, like, for example, here we're exposing them to a pill, and then we're waiting for them to develop a disease. We won't get enough sample size in the time that we need. And even if we do get something, our sample size is going to be really small. So we start with the population that already has the disease. And this is why, since it's a really small population of which has a disease, we can say that the odds ratio are almost similar to the relative risk. So it makes sense to us this way. Does that make sense? Reference group is equal to non-exposed. Depends on what you're talking about. So when you're talking about relative risk, the reference group is non-exposed, yes. But if you're talking about odds ratio, the relative risk is going to be, oh my God, the reference group is going to be diseased or not diseased. So reference group is going to be the control, which is not diseased. Makes sense, Hamza? Okay. So this is basically a phenomena. You just need to know what it means. So Gamder's fallacy. It's a mistaken belief that if an event happens more frequently than usual during a specific time, this event will happen less frequently in the future. So basically, or vice versa. So basically what they're saying is, for example, you're flipping a coin, okay? So you flip a coin 3 times, and all 3 times you get heads. So now you think that if I keep on going with this, I will get more heads than tails. But if you flip a coin 50 times, then you'll have approximately equal number of heads as compared to tails. But like once you are starting out, you believe that, you know, this is like a good luck or something. I'm going to get the same results every time, or I'm going to get similar results more than that. MCQ fallacy. Yeah, there's going to be probably an MCQ on this, like what does this mean? What does this belief mean or something? And you just have to say it's this, you know? So this belief is false in circumstances where what is being observed is truly random. So usually they tell you this, right? Yeah, can arise in many situations, and it's most appropriately, most strongly associated with gambling. So for example, if you see like you're gambling with horses, you know, so you see that this horse is winning a race. No, this is actually not a good example because the horse can be stronger. But let's say you're gambling with dice. So you get like 6 3 times upon, like, you know, throwing the dice 3 times, and you're like, okay, khalas, I'm going to get 6 even more in the future. So you keep on going with 6, and then you lose all your money. You know, that's basically the phenomenon. Similarly, if some people, they have 1 child and it's a male, and then they have another child and it's also a male. So they're like, okay, you know what, the third child, wait, what did they say? It's the opposite. So if they have like male, then they were like, next time it's going to be a female for sure. Same thing with the situation. I made a mistake. Wait, let's go back. So if I keep on getting heads, the next time I think I'll get more tails because I got more heads in the beginning. Okay? Does that make sense? Lol. So something is happening, and then they're like, you know what? Now we get the chance for something else happening. So for example, they got more 6s in the beginning, and then they're like, nope. We're going to get something else now. But they keep on getting 6. Make sense? Sorry. This was so simple that I'm like, you know what? No need to even read this. Anyway, so this is just a concept that you need to know. For example, someone is expecting a male child. They keep on having like 2 or 3 females, and they're like, you know what? Next one, inshallah, male. But you know, it's inshallah. It's not depending on them. Okay, so basically, this YouTube video is the one I used to take snapshots of this. Now, I don't recommend that you go through this unless you are really bothered by the fact that why do we use relative risk? Why do we use odds ratio for these specific cases? Because you know, if you really want to clarify your concept, you can use this, but it may confuse you, so at your own risk. Okay. I added this. I'll share the link with you. Okay. So now we're done with lecture number 1. So now let me briefly summarize everything. So relative risk, it depends on ratios. You compare two proportions together. Okay. So you want to know if, where is it? If the ratio is the probability of disease among exposed to the risk of disease amongst unexposed. So basically you go A over A plus B over C over C plus D. Please tell me I'm correct. Yeah, C over C plus D, okay? Also, this is used for cohort studies, and this is more intuitive. It makes more sense. However, it cannot be used in circumstances where we're going back in time. For going back in time, we use the odds ratio. An odd is something, one number divided by 1 minus that number to 1. Odds ratio is basically we take two odds and we divide them together. They may ask you to work out the odds of something in an MCQ, so just be aware of that. So this example is one that commonly recurs. So if something is the odds of something happening, or the odds ratio or the relative risk is 1, that means it's equally likely to happen in both circumstances. If it's greater than 1, that means that our exposure is the chances of it being exposed and getting a positive outcome, or the chances of developing a disease is, you know, more likely either way. Yeah, that's about it. Yeah, if it's a really small population, or if the probability is really small, then odds ratio can be equal to relative risk. Gambler's fallacy is like somebody keeps on having male children, then he's like, you know what, next one female, and it's not necessary. Yeah, so usually it's for rare diseases. This is why we're using case control. Otherwise, I think it makes more sense to use cohort studies. But that depends on your study design. Yes, we're going back in time, and rare disease, you're right. The key difference between calculating is the total, right? Yeah, so in odds ratio, you don't have the total as the denominator. You have the 1 minus the probability as both of the denominators. So for example, if you have A over here, then you won't use A plus C, you will use A over C for the odds ratio. Okay, now do you have any questions about this? This is relatively easy. It's just like takes a while to understand, but once you get the hang of it, it's really easy. Any questions so far? Oh my God, it took half an hour. Or 40 minutes actually. Anything you're not sure about this until now? Anything you want me to re-explain? The studies, we can solve the question. Yeah, you can solve the questions. Can we solve the question? So which question would you like to solve? Together for odds ratio. Sorry, again, I don't understand what you mean. The coin when given. You want to solve it for odds ratio. But you can't have odds ratio over there, because over here, we're not comparing two different groups. They just used one example in which they have one odds and then they have a second odds. It's not that they're comparing one odds to another, so we can't call this as odds ratio. We can calculate the odds. Yeah, sure. So for example, in this example, they want us to know the odds in favor of getting exactly one tail, okay? So let's just focus on this part. We're just calculating odds, not odds ratio. So over here, we know that these are our total possibilities. Total number of possibilities is 8, okay? Now we want to know the odds in favor of getting exactly one tail. So what are the chances of success of getting exactly one tail is going to be 1 over here, 1 over here, and 1 over here. Everything else has either 2 tails or no tail, okay? So this 1, 2, 3 is the chances of successes. Now we want to know the chances of failures, or 1 minus successes. So we go divided by 1 minus 3. So it's going to be 1 over here means 8. So it's going to be 8 minus 3. because 1 stands for the total set. Oh my God, I didn't explain sets and not subsets. But basically it means, oh wait, actually, if you want to understand in terms of sets and complements, it means you have a subset, which is 3, and then you have another complement of this, which is 5. So you have a set and a complement, or a subset and a complement. Does that make sense? I'm not sure if I should go there. But basically, we take the values that you do have, which are included in one category, and then you subtract them by everything else. So you have these 3, and then you subtract these 3 by the total number, which is going to be 8 minus 3. Yeah, I remember complement. Can I just write this down to make it easier? So basically what we are doing over here is we have a numerator, and we have a denominator. Okay. So for our numerator, we are taking the chances of success, which is 3. Okay. And then for the denominator, we are taking the chances of failure, which is going to be 1 minus p. Over here, it's going to be total minus 3, which is going to be equal to 3 divided by 5. And then if we're going to say what are the odds of this, we will say either it's 3 over 5 to 1, or we say 3 ratio 5. Make sense? This thing over here. I mean, can we calculate the odds? I remember complement vector. So basically what I meant by complement, so that other people are not confused, is basically the denominator is complementary to the numerator. What I mean is, so over here in odds, you see how this is the numerator and everything besides this is the denominator. However, in probability, the denominator includes whatever is in the numerator. And that's the only catch to this, basically. So if we go for the other example, the odds against getting, over here. So the odds against getting exactly 2 heads. So now what we will do is our successes are going to be everything which does not have 2 heads. So our successes are basically everything that does not have 2 heads, which is basically 5. Okay. So in the beginning, we write 5 as the numerator. Okay. And then we want to know what is 1 minus p, which is going to be, so it's going to be p divided by 1 minus p, which is equal to, over here it's 5 divided by 1 minus 5, oh my God, which is equal to 5 divided by 3 to 1. Make sense? The second example. How, oh my God. See, this is why I did not need to use this example. So 1 basically means the total probability. So you know how probability is always 1. So if you have one thing in decimals, if you have something as 0.25, the other thing has to be 1 minus 0.25. In this example, the total is 8. So we have to use 8 minus 5. Okay. Good, makes sense. Move on. So you know how we calculated odds for one thing? It's the same exact things, odds for another thing, and then we use them, like, you know, we just divide them and we get the ratio. Over here, we use odds for this divided by odds for this divided by odds for this, and we get odds ratio. Okay. So let's move on to the second lecture now, which is let's go with this. So the reason why I chose this order of lectures is because the first 2 or 3 lectures are the most, I wouldn't say dense, because Khalid's lectures were dense. These are just technical and they require some understanding. Lectures after this, they're just like you have one concept that you need to know, and then you just basically either memorize or just follow examples to understand what it means. Okay, so this is the reason why I'm going with these. Now, I'm not going to give you a break right now, but I will give you a break after this lecture. Okay, because this lecture is
sorry, but are you able to use the pen if you're going to like do calculations?
Am I able to use the pen? Tell me how I'm supposed to use the pen.
Yeah, right there, pen.
Ooh, fancy. Cool, cool. Let's use this. Thank you for that. Okay, learning objectives, review, scatter plots, parametric, non-parametric, learn two coefficients. Okay, cool. Wow, fancy. Okay, so basically this is a general concept that when you are performing a study, you cannot take the whole population, you cannot take everybody in the population. So what you do is you take a sample, which is representative of that population, and then you run tests on this sample. And then basically whatever tests you run, you infer that this, since this represents this accurately, whatever conclusions we made on the sample will be the same as the population. Okay, so this is basically a review. You covered all of this with Khaled. This is all pre-midterm, okay? Nothing to it. Introduction to correlation analysis. Okay. So over here, the most important thing is something known as correlation. What is correlation? Then we need to know what is correlation coefficient. Then we need to know how we can make sure this is significant or not. And then we need to basically understand if it has anything to do with causation, okay? So there's basically four main concepts in this lecture. So firstly, let's just read this. It is a method that researchers use to measure the strength of relationship between two variables, okay? So basically, whenever we say that there's a correlation between one variable and another, we mean that a change in one variable, how do we say this? If one variable is changing in a certain way, the second variable will be changing in relation to it. So if something has correlation with each other, if two things have correlation with each other, that means variable A moves in a similar fashion to variable B. Now, it could be that variable A is increasing and the other one is decreasing, or it could be that they're not, moving, they're not related in any way. And this is what we're trying to figure out, okay? Okay, so over here, it tells you that correlation, where is it? Correlation analysis determines the cause and effect. Okay, so it does not determine cause and effect. It just tells you if one thing is related to another, or it's moving in a similar way to another. Okay, why does it not tell you about cause and effect? This was the fourth point. Does it relate to cause and effect or not? Because other confounding variables that are not present in the research may have influenced the results, but we did not take those into account. Okay, so basically correlation analysis, whatever correlation analysis is, we can never say variable A is causing variable B, because there could be variable C, D, E, F, which are having an effect on this, but we don't know. Okay, first point, understood? So what I mean is, if we are saying there's like two variables, one is weight, one is height. If we see that both of these are changing together, like height is increasing and weight is increasing, okay? We cannot say that the increased weight causes or has an effect on the height. We can just say as weight is increasing, height is increasing. So they are positively correlated. Make sense? Because the height could develop on the amount of food intake, physical activity, everything else that we did not consider in our study. Does it make more sense now? So what confounding variable means is variables that we did not take into account, but they are present over there and they are affecting the results of the study. So in order to say that something is really having an effect on something else, we have to control literally every other variable that we can. And this is usually done in clinical trials, okay? Because in clinical trials, they try to control every other thing between the test group and the control group. and the only variable that's different is the one that they're testing. So yeah, so they're never dependent upon each other. They may be changing in a similar way, or they may be correlated, but they're never dependent upon each other, or we can never conclude that they are dependent upon each other. Okay, so to measure the strength of the relationship between two categorical variables, we use a chi-square test. Okay, so basically there is something known as a correlation analysis. What is it called? Yeah, I think it's called the correlation analysis. So correlation analysis we can only do between continuous variables. Do you remember what continuous variables are? 1, 2, 3, 4, 1.1, 1.2, 1.2, 1.4. They don't have a gap between them. Categorical are like divided into two groups. So one is like age, one is gender or something. Make sense? So you just have to memorize that for anything that is not continuous, we use a chi-square test. It's just some information out there that may give an MCQ on this. Okay. So the most basic relationship between two variables is a linear relationship. What does that mean? It means that if one is increasing, if one variable is increasing, something is happening to the other variable, which can be represented on a straight line. So you see in the straight line graph all your life, that usually tells you that there is a linear correlation between two random variables which are continuous. Oh my God. Word linear derived from line, ability to represent or express relationship associations between two variables using a straight line. So I'm pretty sure all of you know what this is. This is y is equal to mx plus c in a fancy way. Basically, whenever we have two variables, we take x as the independent variable, y as the dependent variable. Y is always vertical, x is always horizontal. B over here is the slope of the line. We've usually learned this as y is equal to mx plus c, where c or a over here is the y-intercept, and b is the gradient. So this is just to tell you that you can represent this on, whenever there is a linear correlation between two variables, you can represent it on a graph, and it will be a straight line. Okay. So for example, over here, they took the example of one variable being Celsius and one variable being Fahrenheit. So both of these are continuous, right? This is why they're able to plot them on the graph in the first place. So they compare this and they found that there is a straight line. Okay. So that means that there is a linear relationship between them. Now, one more thing, it could be like these points could be varying like this, which is a quadratic correlation. It's not a linear correlation. So if they ask you if something does not lie on a straight line, does that mean it has no relation? No, it means it does not have no linear relation. It could have other relations, okay? Could be a cube or something. Make sense? Okay. So suppose we are interested in a pair of continuous random variables. Continuous, again, is important. From the same set of patients, for example, the study has on the x-axis, okay, important to note, on the x-axis is always going to be the independent variable. So over here, it's the amount of tetanus in a specific population. Is it? Immunized. Who have been immunized against. Okay, so basically immunized because this is what they had control over, you know? They could immunize people. And why was the corresponding mortality rate? They can't control the deaths. So dependent or independent is always going to be X. Over here, independent is immunization because we control it. So any independent variable is in the hands of the experimenter. Any dependent variable is what we're basically trying to measure, or it's something that we're trying to see, which is going to be the mortality rate. Mortality rate, by the way, means the number of deaths. So basically, they are taking a number of children who they have vaccinated or immunized against tetanus, and they want to see if this is increasing the number of deaths, or is it decreasing it, or does it have no effect? So this is what they do. Tetanus is a condition which causes contraction of skeletal muscles. It's caused by this bacteria. Just memorize the name of this bacteria because sometimes they bring this stupid MCQ which has nothing to do with biostat, but it's there in the slides. Yes, X is independent. X is in your hand. Whatever you plot on the horizontal axis is under your control. Over here, what we have under control is the people we're vaccinating. We cannot control the number of deaths that occur. Okay, so that is placed on the y-axis. Data for random. Okay, so they took basically data from 20 countries. So they had this data, and then what they did was they plotted on a scatter plot. So two-way scatter plot means that you have an x-axis and you have a y-axis. So this is what they did. So now over here, whenever they give you a scatter plot and they want to determine if there's a relation or not, a linear relation or not, you draw something known as the line of best fit. Do you guys have the concept of this line? Okay, I'll tell you in a bit. Do you guys know what the concept of line of best fit is? Okay, so basically it's an imaginary line. So you want to see if you can make a straight line between these or not, right? So what you do is you draw a line, you make sure that it's between all of these variables. And the idea is that the distance of this line, there's like the minimum distance between all of the plots and this line. So you'll draw the line in such a way that the distance between this line and all of the other variables is minimum. Okay? Does that make sense? Okay. Basically, if you can draw a line, okay, you know what? Just hold this concept for now and I'll talk about it later, okay? But basically you draw a line of best fit, and if you can draw a straight line, that means that there is somewhat really linear correlation, okay? Do you mind repeating? Yes, I'll repeat it in a bit. Okay, so basically independent. So you see independent over here is on the x-axis. What does independent mean? Independent means it's not depending on any other variable. That means it's under my control. I am the experimenter. That means that if it's under my control, that it should be a variable that I am, I have control over, and I have control over immunization in this case, because I am vaccinating people in 20 different countries, okay? And we want to check the mortality rate, or how many people are dying even after being vaccinated. This is dependent on the vaccination, as in we do not have any control over this. This is dependent on either vaccination or some other variable, So we put that in the y-axis. Why do we do that? It's just, what do we call it? It's just the way like they first thought of doing it. What do we call it? Conservative? It's just the way like they started plotting this from the beginning, and this is how we just follow it, okay? Line of best fit basically tries to represent the general pattern of the points in the graph. It doesn't necessarily go through them all, but shows you the pattern. Yes, perfect. You summarized it accurately. So response would be dependent. Yes, the response is dependent. Basically, we plotted the two-way graph. We had x-axis values and we had y-axis values. Y-axis was the dependent. Yes, it is the response. Okay, so examine the previous plot and make your conclusion about the relationship between mortality rate and the children of the percentage of children immunized. Okay, so basically, if you have a line which is basically shows that the y-axis or the dependent variable decreases as the independent variable is increasing, what is this? Positive or negative correlation? Yeah, negative, because one variable is increasing, the other one is decreasing. So in this example, what did we have? Positive, right? Yes, thank you. Okay, so you see over here, it says, is the relationship between mortality rates and the percent of children immunized linear? So is it linear? Can we draw a straight line and somewhat depict the data? Yes, we can, okay? If so, quantify the strength of the relationship. Okay, so you see this part, we just know it's positive or negative. We don't know what the strength of this linear relationship is. when we want to check out the strength, we use something known as correlation analysis. Okay, we use something known as correlation coefficient. This thing gives you the strength and direction. Plotting it on a scatter plot and looking at the general trend only gives you the direction of negative, positive, or no relation. This basically means that like if it's a horizontal gradient, that means that there's no relation. If it's a vertical gradient, that still means that there is no relation. Okay. Okay. Okay, this is an example that they want you to do. Don't get into this. This is what they plotted, and then they drew the line of best fit, which you can see. Examine the previous plot and make a conclusion about the type and strength of the relationship between this. So basically, what do you see? Is it positive or negative? Yes, thank you. Okay, so now let's talk about correlation coefficient. Okay. So two variables are said to be correlated when a change. Oh my God, where's my cursor? Cool. So this line is important. Two variables are said to be correlated when one of the change in one variable is accompanied by the change of another variable. Basically, the definition of what correlation means. The correlation coefficient measures the extent to which the two tend to change or correlate. So you see, extent is basically the degree of correlation, and this is why we're using the correlation coefficient. It measures the degree to which changes to one value of one variable predict changes to the value of another. So you see, they're using the word predict over here. They are not using anything that is anything similar to like cause or effect or causes or results in. Okay, it's just predicts, because we're just predicting. Isn't that just the slope with the extent? No, it's not, and I'll tell you why exactly now. So in other words, correlation gives you two things: the strength and direction. Okay, and the other thing is that's really important is linear. Okay, so you have two types of correlation coefficients that's included in this course. So one is the Pearson's correlation coefficient, and the other one is Spearmint. So we're just going to talk about Pearson's. Okay. Spearman's, we'll just give you an example at the end to tell you the difference between these two. Just to give you a flavor of this is a parametric measure and this is a non-parametric measure. Okay, but it's exactly the same thing or exactly similar to each other. So now let's talk about the Pearson correlation coefficient, which is represented by the letter R. Okay. This is the most important thing of this lecture, okay, because there's going to be an MCQ that's going to ask you to calculate this, if not more MCQs, you know. One of them is always going to be a calculation. So basically, it evaluates the linear relationship between two continuous variables. Continuous is important here, linear is important here, two is important here, I think. Estimates correlation to population. So over here, it's the same idea that if there is a correlation between the sample, then you can relate it back. You can infer that the population will also have this. Okay, and it quantifies it. Okay, so what you need to know about R is the following things. Once you have calculated R, and I'll show you how to calculate it, it has no units of measurement because the units are divided over each other and they cancel out. Okay, they cancel out. Now, the maximum value of R can be 1. It can't be greater than 1. If it's more than 1, your answer is wrong. If it's less than -1, your answer is wrong. 1 means that there is an exact positive linear correlation between this. Now, what does R mean exactly? So you know how we said there's a line of best fit? R basically tells you how close the points are, each individual point is, to your line of best fit. Okay? If points lie exactly on this line, if all of the points lie exactly on this line, that means you have a perfect correlation, either positive or negative, and that means that you have the value of 1. Okay, so for example, over here, if you measure R, it will be negative something. Negative because it's a negative relation. It won't be 1 because all of the points are not lying on the line of best fit. So in answer to your question, Iman, the line of best fit basically tries to represent the general pattern of points on the graph. Yes, it does. And then somebody else asked, isn't that just a slope? No, it's not a slope. Who asked this? Iman as well. isn't it just a slope? No, because we're not measuring the slope over here. We are measuring the extent to which how close the points lie on the line. So if we look at this example here, what would be the R value? Yes, +1. The slope gives you an idea of the extent too, right? No, the slope basically tells you how much both of these variables are changing proportionate to one another. For example, if one is changing by 10, is the other one changing by 10, or is it changing by 20, or is it changing by 30? That's what the slope tells you. But over here, we want to know how similar the changes are. So for example, if you have a steep slope like this, it would mean that they're like, if all the points are lying on this same line, it means that, okay, fine, Fahrenheit is changing a lot more as compared to Celsius, but the proportion of them changing is going to be exactly the same. Or, yeah, that's the best way to say this. The proportion of these changes are going to be exactly the same. For example, if there was a change in 10 over here, there's always going to be a change in 20 over here. Does that make sense? Now I'll tell you how we're calculating in a bit. The steeper the slope, the stronger the relationship. No, it's not. Scatter plot is linear relationship that gives only direction right. Scatter plot basically means you have you have this graph and you have an x-axis and you have a y-axis and you're plotting stuff on this. That's what a scatter plot is. So basically a line graph, I think that's what you meant. A line graph tells you if it's a linear relationship or not. Yes. Can you repeat the Pearson? Yes, I would. So basically you have a set of points over here, okay? Now you draw a line of best fit. Okay, you drew this line of best fit. Now you want to know if all of these points, like how close all of these points lie to it. If they lie really close together, you will get a value. Wait, let me go to that slide so it makes sense. Okay, so for example, if you have a line and all the points are similar to each other, since this line has a negative gradient, this is going to be negative, okay? And it's going to be really strong since all the points are close together. Whereas if you have a line which is the same gradient, but the points are further away, this is going to give you a negative correlation because the gradient is negative, but it's going to be weaker because the points are further away from the line of best fit. Does it make sense now? Okay, so basically you can have something known as a positive coefficient, which is going to be from a positive value, which is going to be either 1 or less than 1. Same thing for a negative value, less than 0, but not less than -1. If there's no linear relationship between them, then R is equal to 0. However, that means that a non-linear relation, like a quadratic or a cubic or a hyperbolic, whatever relationship may exist. But this correlation coefficient is only for linear relations. Yes, weak would be further away. So now honestly, these numbers, just memorize what categorizes as strong, because they can bring you really weird MCQs. So just know that if it's more than 0.8 or less than 0.8, it's going to be strong. This is moderate, this is weak. Because they might ask you something like, okay, so for example, you have -0.4. What is it? Is it negative, moderate, negative, strong, or negative, weak? I don't know why they're doing this. Makes no sense, but they're facial exams, Just weird like that. Okay, so now calculating R. Now this formula you have to memorize. I am sorry, you have to memorize this, okay? And there's going to be a question on this 100%, okay? So how do we work this out? They explain it to you. Basically, and I'll explain why you have to memorize the formula. So you see this is how you're going to work it out. Basically, you will have values on the x-axis, you will have values on the y-axis. First, you find the mean, which they do over here, the mean for both. Then you subtract each value by the mean, Same thing, they subtract each value by the mean. Then these two values, they multiply together because they're fancy like that. And then they put that as the numerator. after adding all of it up. Okay? Then they do the same thing for this, but what they're doing over here, you have to be really careful. They're taking this and they are just squaring it. Okay? So whatever answer you get over here, you square it and you get this. And then whatever answer you get over here, you square it and you get this. Okay? And then you basically fit them over here. Now it's really important to remember this value is just this. These values come from here, and there is always a stupid under root that everyone forgets. Okay? Now there's going to be one question in the exam which is going to be about this. And the working goes like this and on and on and on. It takes you 15 minutes to do this. Not worth it. So what I basically came up with was, you all have a calculator like this, Casio calculator. Basically, Dr. Hassan, or at least Dr. Peter, he allows you to use the calculator in the exam. These awesome calculators can calculate this in 2 minutes. Okay? The only trick is that your BLT needs to convince Dr. Hassan or Peter to use this. We're not allowed to use a calculator. Oh, they will allow you, for sure they will allow you to use this. No, you have to convince them. So for us, we were 10th batch. Okay, we talked to Dr. Peter, we were like, please, please, please allow us to use this. We can't calculate on this thing, it takes too long. He was like, yeah, sure. Dr. Hassan, we didn't approach because we weren't sure. 11th batch, they got it in their final as well. They were able to use calculators. So this time, it's for infection control. Try to take it. Try to convince him to take it. Yeah, I know, but the ExamSoft calculator does not have this. It's really stupid. Convince them, yeah, your BLC, he goes and puts up a good argument. Doctor, please, we'll use our own calculators, blah, blah, blah. We'll sanitize it before, after, whatever you need to do. No, the ExamSoft one does not have this function. Yeah, I'll show you. Okay, so basically in the midterm, you had standard deviation, right? So this is the one for midterm or pre-midterm. This is the one for post-midterm. So I'll play this video for you because I just want you to show you. I just want to show you the ease of this. The problem was in our exam, we were allowed to use this calculator. The thing is, I forgot how to use it in the exam. You know, how to calculate this in the exam. And that bothered me so much because I had to spend the 15 minutes on it, and honestly, we did not have time. And like, I barely finished. Okay, do you guys have the slides open with you right now? You guys, oh my God, you can't hear the, why can you not hear this? What? Give me a second.
I think there's an option if you stop sharing and then share again. I think there's a small checkbox in the where it says share computer sound. Not share. Okay, yeah, just like Iman says, go to the top.
And then we want it in this one that says A plus B. It says the heights and arm spans of 10 senior students are shown in the table below. And we want to calculate the correlation coefficient to 3 decimal places. So the first thing we want to do is put your calculator in statistics mode. So you can turn it on, mode, stats, so you're going to press 2. And then we want it in this one that says A plus BX, so we'll press 2 again. So this gives us this column. So the X column is going to be our heights, and the Y column is going to be our arm spans. So we'll go enter all our heights first. So we've got 160, and then press equals, and it'll enter it in there. So you can go through and do all of your heights. Okay, so we've got 10 heights in there, which is what we wanted. Now we need to enter all our arm spans next to the right ones. So we need to make sure we do them all in the same order. So we'll go back up to the top and go across, and we'll enter them in. So next to the 160 needs to go 162. So 162 equals, and we'll go across. Okay, so we've got all of our data in there now. We can press our AC key to get out of the table. Right, now we want to get into where we can figure out all our different little statistical facts about it. So above the number 1 key is written the word stat. So we're going to go shift and stat. We want to go into the one that says reg, so 5. And then we want this R, because we know that correlation coefficient is represented by the letter R. So we'll press 3 and then equals. And it will tell us that our correlation coefficient is 0.965, correct to 3 decimal places. So that's a really strong positive relationship between height and arm span. Okay, so that's how to calculate the correlation coefficient with your Casio calculator.
Hi, can you guys hear me now? Okay, perfect. Okay, so you can watch this again on your own time. I want you to watch this again on your own time, and then I want you to practice as well. The problem is, what is this? Yeah. So the problem is, you want to practice on an example that's not done before, right? So either you can use the example in the video, or you can use it on this example, which is what I recommend you guys to do. So use it on this example, and then I'll give you the answer at the end. I'll tell you what the correct answer is, and if you get it right with the calculator, khalas, you got this. Now, this is why I'm asking you. Why is everything so pixelated, really? I don't know. What's wrong? Can you see now?
How about you stop sharing and then try again? Maybe that could work.
Better. Can you guys hear me properly? Because I'm afraid my internet is going to start having spasms. Okay, so if this, in case this comes in your exam and either you're not allowed the calculator, or like in my case, you forget how to use the calculator, you need to at least remember the formula, and you need to be able to manually work it out. So it's going to be only one question, and it's only going to be worth 1 mark at the end of the day. So what you do is you leave it to the end. As soon as you see this question, you mark it, you leave it towards the end. Then at the end, if you have time and you are done revising and you think that you don't need to revise, like you have 15 minutes, start doing this question. Otherwise, like people in my exam, they just gave up hope and they were like, you know what, bismillah, eeny, meeny, miny, mo, yallah, It's 1 mark, exactly, it's 1 MCQ. So this is why I'm saying use the calculator for this it doesn't make sense that you memorize this. The other thing they can do is, which they most probably won't do, but they can, like, give you variations of this formula and tell you which one is correct, which is like, if they do this, it's like the stupidest question they can come up with. This is why I'm just saying, let's memorize the formula in case you need it for this or that. Also, wait, I think you guys get a formula sheet. Please confirm this. Yes, you do. Okay, perfect. So then they won't bring a question like, which is the correct formula, or at least like that'll be stupid. But anyway, you guys need to know how to work it out in case you have to manually work it out, in case you want that 1 mark, in case you really want the A. Yeah, you'll get one. If you got one in the midterm, you'll get one for sure, inshallah. The only thing is, try to convince Dr. Peter that you need your calculators, you will sanitize them, whatever you want, because on your own calculator, it's a lot easier to use all the other calculations as well, to do all the other calculations like ratios, relative risk, whatever, So it's always better to have your own calculator. You can tell them we'll remove covers, we'll sanitize it before, after, whatever you have to convince them. But I honestly think it's better if you have your own calculators. You can put in your bags 5 days earlier if you're like thinking it's a code or something. So a correlation is a technique that is used to investigate the relationship between two quantitative continuous variables, for example, age and blood pressure. Pearson's correlation coefficient measures the strength of linear relation between two variables and the direction of this relationship. Okay. To research the relation between variables, you can use surveys or questionnaires. So this is basically telling you how you can design your study. Just read through it. There's nothing to it, honestly. You plan to test the hypothesis that passive smoking causes asthma in children. Passive smoking or secondary smoking is inhalation of smoke by persons other than the smoker, okay? Is it ethical to conduct an experiment to test this hypothesis? Is it ethical to deliberately expose children to passive smoking? No, it's not. How to test this hypothesis? Conduct a correlation study, find out if children who experience smoke are more likely to, okay. So basically they're telling you over here, they're telling you you have to conduct a correlation study. That's the only point of this, because the other way of doing it, like inducing smoke to children, is not ethical. That's basically it. Okay, so once you do a correlation study, you have to figure out if the correlation, like if there is a strong positive or negative correlation between the two variables that you have, right? So basically you go for the Pearson's coefficient, okay? Now, what are the limitations of R? And you have to keep this in mind because they can ask you in MCQs easily. So R quantifies only the strength of linear relationship. It does not quantify non-linear relationships. Secondly, it's highly sensitive to the presence of outliers. What does outlier mean? It means, like, for example, you have a lot of values which are similar to each other, and then there's one value which is far away. So for example, all of these values are similar to each other, but there is this one value which is like far away. The idea is that if you draw a line of best fit, since it has to be the minimum distance from each of these, this one outlier can pull the line towards itself. So it will result in a, it will affect the results. Basically, it will result in a skewed R value, okay? Okay, so it also says R should not be extrapolated beyond the observed ranges of the variables. What does extrapolated mean? Extrapolated basically means, yes, since it affects the mean, and if you check your formula, it has a lot of means in it. So basically, extrapolation means that you have these values, right? Now, you think that if you have some more data which lies somewhere over here or somewhere over here, it will be similar to this because you just extended the line. This extension of the line of best fit means extrapolation. And basically, you're assuming that the other results that you have rely on this. You cannot do this with R when you're measuring for R because you can have outliers. So you cannot extrapolate results and say, we conclude that the trend will continue because this is a correlation. No, you can't, okay? Yeah, okay, so it does not specify a cause and effect relationship. That is to say, if two variables, cigarette smoking and lung cancer, are simply correlated, it does not in itself imply a cause and effect relationship. Okay, cause and effect relationships are usually done in randomized clinical trials because they control all other variables except the variable that you are measuring for, okay? Now, non-parametric statistics. Now, this is known as Spearman, okay? Spearman starts with an S, has a tiny s over here, okay? So it is, why do we need a Spearman rank test? Okay, so first thing you need to know is it has the word rank in it. Second thing you need to know is that we have to use this in cases where R alone does not work, okay? So what does this do? Basically, it takes all of these values. It takes all of the values of your data, for example, over here, and it ranks them, okay? So it'll rank them according, like it'll arrange all of these in order of least to greatest or whatever, and then it'll rank them according to their value, okay? And it'll rank both of these. How does that help us? If there's any outliers, for example, an outlier over here was like 200, if you're ranking this, it will just be one rank above 119. So for example, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So these are 12. So this one will be rank 13 because it's like, you know, higher than rank 12. But it, like the difference between 12 and 13 is only 1 as compared to the difference between 119 and 200. Does that make sense? This means that outliers will not disturb it. It doesn't? Okay, wait, I'll explain again. So for example, over here, you have this data, okay? You have 1, 2, 5, and then you have 3, 9, 12, 15, okay? Now these values are similar to each other. Now, for example, you have something 6 over here, and over here you have 500, okay? Oh my God, my internet. Can you guys hear me? Okay, so my internet just told me it's unstable. So at any point, if my voice cuts out, please let me know, okay? So for example, this value is 6 over here, okay? And this value is 500. Now, if we plot a graph for this, instead of being like this, since there's an outlier, the R will be shifted upwards and it will go over here, right? However, if we take this data and we rank it, so we go 1, 2, 3, 4, and 5. Oh my God. This last value will be 6. Now the difference between 5 and 6 is similar to the difference between 3 and 4 and 1 and 2. However, the difference between 12 and 15 is not similar to the difference between 15 and 200. So the gap over here, if we're plotting just this data, is going to skew the results. But if we're using the Spearman rank test, where we first rank the values and then we apply this formula, or a formula really similar to this, the outlier will not have an effect. Does that make sense? Yes, so Spearmans, you're going to first rank all of your data. Yes, you're ignoring the data, you're ignoring the values of the data, but you're not ignoring the trend of the data. The trend, by trend, I mean 15 is still going to be less than 500. Yes, we use the rank numbers, exactly. So first we're going to rank the data. After we are done ranking the data, we will apply the same formula or a similar formula. I'm not sure if it's going to be exactly the same or not. And you will get a value, because over here, you are not trying to see how much one value varies with another. You're trying to see if this value varies 3 times. Does this value also vary like 6 times or 3 times or 9 times? You just want to check, is the relationship between these two proportionate or not? If we use the rank, we won't ever have the same R. No, not necessarily. So it's just the numbered values in order, and we're finding the mean for the data set. numbered values in order. Well, they're ranked, so they're not technically in order. This data, by by coincidence, is ordered. So for example, if you're going to rank this data over here, your rank will be different. For example, where is my cursor? Okay, so this is, for example, 13. Okay, this is going to be rank 12. This is going to be, where is the least one? This is going to be rank 1. Similarly, the ranks of this, but they're not changed in order, you know? So this is going to be rank 12. This is going to be rank 11. So once you calculate the R, you take this data set as like one data set and this data set as another data set. So the R value, it does not like change a lot. It's going to be relative to, the RS value does not change. It's going to be relative to the R value. Does that make sense? Because we're not changing the order of the rank. We're not changing the order of the numbers. We're just ranking them. You know how you go like he got 200, he got full in the exam, and then he got first place. Still means he got the highest one. Like, it's not ascending or descending order. It's just, well, it's ascending order obviously. It's ascending order obviously, but like ascending order, like the smallest value is going to be 1. The largest value is going to be the largest number. So the R value should always be the same for data sets within the same number of values, right? So the R value. So the R value should always be the same for data sets with the same number of values, right? No, it would not, because okay, first of all, there's a difference between R and RS. If you have one data set, you will get one R value. If you have the same data set, you rank it, you will get an RS value, which will not be similar to the R value. They're two different things. Okay, sure. So the RS value should always be the same for data sets with the same number of values, right? No, again, because the data set does not depend on one variable. It's a set of two variables that you're taking as the X and Y axis. You know, so once you plot it, it'll depend on rank of X value and rank of Y value. So it's not necessarily going to be the same if you have the same number of values. Okay, never mind, I get it. We decide how we're ranking. So we rank it different, it's different. No, ranking is always the same. The method of ranking is always the same. The least value gets 1, the one higher than that gets 2. Yeah, I guess I have to do an example, that's fine. Okay, so let's go with this example. Okay, so for example, we have this. Okay, now we want to rank this data, okay? So how do I do this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, that should make sense. Okay. So for example, we have this. Okay, now we're going to rank these numbers. So what's the least one? It's going to be 1, 2, 3, 4, 5, 6. This is the smallest one. So 1, 2, 3, 4, 5, 6. So this is rank 1. Okay. Now rank 2 is going to be this. Then rank 3 is going to be this. Then rank 4 is going to be here. Rank 5 is the last one. 6, 7. Really? 7. I missed the rank, did I? 1, 2, 3, 4, 5, 6, 7. So basically 10 goes here, then it goes 11, then goes 12. Okay, can you guys see? Oh my God, really? 5, 6, 7. Okay, fine. 8, 9. Oh my God, I can't even read this. It's a disaster. I'm going to waste some of your time now. 1, 2, 3, 4. Or no, 4 is fine. 5. Yeah, so oh my God. Okay, sorry. Let me explain. So you see which is the smallest value from all of this? It's 81, right? So basically I'm ranking, yeah, you know what? It's going to be a lot easier if I just annotate on top of this. So basically I am ranking, oh my God, this makes it a lot easier. I'm ranking this as 1, this as 2, this as the 3. Then we go 4, then we go 5. Okay, now 6, 7, 8, 9, 10, 11, and 12. Okay, now let's go back and read what you were saying. Okay, so someone got how they decide ranking. It was Iman. I guess we do an example a bit clearer. Yes, we're doing it. Yes, please, can you explain how we rank? So basically, I looked at all of these values and I arranged them in my head from the least to greatest. So least, I gave them rank 1, then rank 2, then rank 3, and accordingly, okay? So the beauty of this method is, for example, if I have a value which is 500 after this, 500 after this, in the ranking, its rank will be 13. Okay, so even if it's an outlier, if we consider the ranked data, it won't be like this. So I'll do the same thing as for this, ranking them, okay? And then I will apply, I will use the ranked data as the rank values as the X value and the ranked values over here as the Y. The only difference is I will not call the R anymore, I'll call it an RS. Does that make sense? How do we rank? So basically least to greatest, 9 is on top, 10, I'm confused, 10 is 11, no 80, so the lowest value has the highest rank. The lowest value has rank number 1. So the reason why I'm using lowest value for rank number 1 is because the number 1 is like, the lowest number from the ranks, and the ranked value is the lowest as well. So do it like this. Use the lowest value as rank 1, because if you do it opposite, it'll just confuse you guys. I mean, technically, if you take rank 1 as the highest value and you take like the last rank as the lowest value, provided that you do it same for both, it should be the same, but your R will be negative, you know, because instead of this, it'll be the exact same value, but your R will come like this if you rank them the other way around. This is why I want you to take the smallest number, 1 for like the smallest value. Does that make sense? Then we do that table. Yes, we do that table calculation. What else did someone ask? So the lowest value is the highest rank. Yes. Rank over here does not have an intrinsic value. It's just that we are, like, you know, it doesn't mean one thing is better than the other. We're just numbering it so that the outlier goes away. Think of it that way. Oh my God, how do I move? Okay, cool. And of course I have to clear the ink. Okay. Yes, yes. Okay. So we calculated this, we went to Spearman, okay? So basically it uses ranked values rather than raw data, and this is why it is not sensitive, or it is robust against outliers. To calculate this, you need to rank the two values separately and then calculate the coefficient of the rank correlations. RS is simply the Pearson calculated for the ranks values, okay? RS is classified as a non-parametric method, okay? So basically just memorize the Pearson starts with a P, and that is a parametric. The reason why I'm saying just memorize is because you don't have that lecture with you. So this is all the detail you need for this. This does not start with a P. Spearman does not start with a P, so it is non-parametric, okay? So like Pearson, it ranges from -1 to 1. Values close to 1, -1 are high degree of correlation. Value near 0 imply a lack of association. Okay, so you know how we rank the data? It has two uses. One is it is not sensitive to outliers anymore. The second benefit is that ordinal variables can also be evaluated. What does ordinal variable mean? Someone yellow. This was lesson 2 or something. Yeah, exactly. Exactly. So stages of cancer and stuff like this. So we can take real world data, which is not necessarily numerical, and we can convert it to ordinal data since they're ranked. So we have somewhat an idea, okay, this is higher than this, this is better than this. We can do a Spearman coefficient on this, and we can get a value of the degree of association between the two variables, right? Okay, so over here it says the same thing. It's a good idea to examine the relationship between variables on a scatter plot, which means just a graph. So even if the correlation is 0, it could indicate something like this. Okay, next. Okay, yellow, answer. 1, 2, 3, or 4? Yes, strong positive. Next. Yes, this one. No, it's what? No, it's memorization. No. if it's negative, it means it's negative. If it's less than 3, it means it's weak. If it's between 3 and 7, it means it's moderate. If it's 8 or more, that means it's strong. This was a table in the PPT. Yes, this was this table in the PPT. Oh my God. This one. Oh my God. Yeah, this one. Yeah, you memorize the values. Yep. Okay, this one. 1, 2, 3, or 4. Yes. Okay, so over here, they didn't mention the R value, right? So you cannot tell if it's strong or weak. You can just say if it's positive or negative, okay? That's the idea. Okay, same. Okay, So now we talked about two things. One, is there a linear relationship or not? Number two, what's the extent of the linear relationship? Now, number three, which you don't have to calculate, you just have to understand the concept, is this correlation statistically significant or not? Now, how do we check for that? Basically, we can make an inference. Oh my God. We can make an inference. So it's the same concept. You are calculating the correlation coefficient of your sample, which is R, and then you will apply it to your population. So this is basically nothing. The main objective is to detect if the linear exists. Okay, they're done with this. Over here, yeah, okay. So over here, the idea is you will take the R value, that you get, and then you will apply a t-test on this. How you will apply the t-test is not important. The idea is you will apply a t-test, and if your value is less than if your p-value is less than 0.05, that means that you will accept or you will reject the null hypothesis and you'll accept your alternative hypothesis, okay? And I will explain this in a second, okay? So over here they calculated the R, okay? And after they calculated the R, they were like, appears to be a strong negative linear relationship, blah, 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 okay? So they only got this much. Now, is it statistically significant or not? So the null hypothesis they took was, there is no such correlation in the population, okay? So that's H is equal to 0. So H1 is that, define the null. Okay, so you have to memorize what the null hypothesis is. So null hypothesis is that relationship in the population is 0. Okay, and if it's not 0, that means that a relationship exists. Either it's positive or it's negative. Okay, so this means that R is equal to 0. I know they wrote P over here, but this is because they're checking for the population. The way they check for the population is basically they look at their sample, which is R. Okay, so R is for Pearson correlation of a sample, and P is Pearson correlation of a population. Okay? Yeah. So over here, they're just going to give you the level of significance. So basically, you have this fancy formula, which they will apply for you. I don't even think they'll test you on this because I never got a question on this, and neither did any of the previous batches. But the idea is you will apply this fancy formula, and then you apply this fancy formula, and then you will get the t-value after applying all of this, okay? Once you get the t-value, then you know how you go to the chart to check if your t-value, like you know the degrees of freedom, you know the t-value, and then you check the p-value, and you see if it is less than 0.05. Everything you did in the previous stuff. Okay, what are you guys on about? No. Listen. There's a t-table. So the one that Khalid explained to you like yesterday. There is one t-table which has a t-value, and then in that t-value, there's something known as the level of significance, 0.05. If anything is less than that 0.05, that means you accept the hypothesis, or like you reject the null hypothesis. Does that make sense? Are you with me so far? Yeah, okay. So basically, you will get a t-value. Then you will look at the chart that you have. If it's less than 0.05, you will say that the correlation is also statistically significant. But if it is more than 0.05, you will say that, okay, there is a correlation, there is a strong positive correlation, but it is not significant. That's it. That's literally it. Nothing else. Don't be confused about P and T values. P over here, this P over here is basically from the T table, okay? This is what I meant. We hunt for this value in the table and we find the P value, right? Yeah, okay, so you don't have to be confused. This P is rho, okay? I think, if I remember my physics correctly. This stands for rho. This basically means the Pearson correlation or Pearson coefficient for the population. Pearson coefficient for the population. Over here, they tell you this. So R is for your sample. If you take the same R, but you apply it onto the population, we will represent it with this letter, which is rho, which looks like a P. Okay, that's all they're saying here. Don't be confused, please. Okay, now one more thing that they may ask you is what will be the degree of freedom over here? You remember the t-test? What will be the degree of freedom? So over here, the degree of freedom is going to be the total number of values that you have. Over here, they had 20 countries, if you remember, and you will subtract it by 2. Nope, over here, it's 2. This is the only difference. Why is it 2? I do not remember the exact reason because Khalid explains this lecture and I didn't revise it for 2 weeks, but the idea is since there's 2 different variables, in all of the thesis you had earlier, I think there was 1 variable. That's why you had 1 degree of freedom, like -1 degree. Yes, there's 2 samples. Thank God Khalid explained that one. Otherwise, I could have just explained this and moved on. Okay. So over here, these are some useful links. This is for the R. Please try to convince your Dr. What's his face? Peter, to be able to let you use the calculator and this. Okay. So do you have any questions about this specific lecture? So positive correlation basically means if one variable is increasing, for example, Celsius, over here it's increasing. For the corresponding value of this degrees Celsius, what's happening to the values of Fahrenheit? So if you go over here, this is 5, this is 40. This is 20, this is 70. This means that as Celsius is increasing, Fahrenheit is also increasing. This means that this is a positive correlation. If one variable is increasing and the second variable is also increasing, that means it's positive correlation. Correlation, the word itself is really simple. It means co means 2, so 2 variables. Relation, are they related in some way or not? When we say they are positively correlated, it means one variable is increasing and the other one is positively increasing with it. When we say negative correlation, it means one variable, our dependent variable on the x-axis, is increasing and the other one is negatively correlating with this, or it is changing in a negative aspect. Does that make it clear? Yes, yeah, yes, inversely proportional. Oh my God. Yes, exactly, Hooke's law. Okay, do you guys have any questions about this one, this topic in particular? If you don't, say no, so I know. If you're still confused about anything, please ask me. Do I continue? Or do you guys want to break? Okay, cool. I'll give you guys a 10 minutes break. The good thing is that we are done with the hard stuff. Now, all of the other lectures, we can probably finish in 1 hour, maximum 1 hour, or like 1.5 maybe. We are left with 4 more lectures actually, but the other lectures, they're honestly really easy. This is the only long lecture. Sampling theory, it's only long because of the number of slides. There's not much content to cover in this. And the lectures after this, it just takes like 5-10 minutes max to explain. So up to you guys. I think I'll give you guys a 10-minute break right now so that you guys can, like, you know, chill, relax. And then I'll cover everything in like an hour max, okay? Yeah, we'll continue at 9. So go ahead, take a break. Are you guys ready? Okay, so just let me summarize the previous lecture really quickly. Basically, I'm just going to read off the important points from my notes because they're so concise. Okay, I love my notes. I'm biased. So categorical variables. In the first slide, it said we use a chi-square test. Just memorize that. If it's continuous variables, we use correlation and regression analysis. Linear correlation is the degree to which two variables, which are quantitative and continuous, are related, and we can express this on a line graph. Y is equal to mx plus c. X is the independent variable, y is the dependent variable. Basically, it tells you if it's a positive or negative correlation. The correlation coefficient gives you an extent to which how much the two variables are linked to one another or how they change together. Tells you the strength and direction. If r is equal to 0, that means there's no linear relationship. It could be non-linear. R can only be between +1 and -1. There's a formula that you need to know how to work out. I think they'll give you the formula sheet, so you don't have to memorize the formula itself. Limitations of R are important. It can only be used on linear variables. It can only be used if there are no outliers present. For a linear relationship, it does not specify cause and effect. It cannot be extrapolated, and it cannot be used if the variables are not continuous. We use Spearman, which is the same thing as Pearson's, but it's for ranked values. It can be used for ordinal or continuous data, and it is known as a non-parametric test. It's less sensitive to outliers. For testing, the p-value or the r-value, by p I mean rho, which is for the population, or the r value, which is the Pearson's coefficient for the sample. We do a t-test on it, and then we see if it is less than 0.05. We say it's a positive, which we say it's a significant correlation. And also the degrees of freedom is n-2. Okay. Please share pics of your notes. So I sent it to Ijaz, and he's not connected to the microphone right now. If you give me an email address, I can send it to you guys, and you guys can spread it out if you want. The only thing about my notes is that my handwriting was for myself because I made these notes for myself. So I'm not sure if you'll be able to get everything, you know. That's the only drawback. The second thing is with my notes, you have to be careful that you don't study stuff which is not included for you guys. For example, this parametric and non-parametric. This is a video for the class Viz calculator. I don't know what that is for. Ah, okay, that's what you mean. Okay, cool. You want to start this now? Introduction to sampling theory. Okay, Bismillah. So this lecture has, now I'm just going to tell you what's important in the lecture, what you need to understand, what you need to memorize, because now all of the technical stuff, all of the things related to numbers is pretty much covered, you know, by Khalid and these previous two lectures, okay? So basically what you need to know over here, the main ideas are this: types of bias. So you need to know the definitions. If they give you questions and ask you what type of bias this is, you need to know this, and how we can minimize this bias, okay? These three things you need to know about bias, okay? And then you need to know types of sampling techniques. So there are 4 types of random sampling techniques, and there's only one type which is covered here of non-random sampling technique. You need to know what that is, basically have an idea about this, and they may give you examples and ask you what type of sampling this is, okay? That's literally it, okay? Yes, that's literally it, okay? So it starts with the same idea, same basic concept. You have a population. You don't have time to experiment on the all of the people in the population, so you pick a sample which is representative. The most important thing is that your sample has to be representative of the population so that the conclusions that you draw are valid. Okay, so this is a review. Representative sample. Okay, so this is basically the type of questions that you can expect, right? And okay, let's read this. The public health officials at the Ministry of Health in Riyadh wish to evaluate vitamin D levels in city residents. Okay, to create a study sample, they selected a random sample of families. Okay, so you know it's random sample in this city for the study. This is example of what sampling scheme. So remember how I said these are the type of sampling you should know? You should basically be able to tell what this is. This is the type of questions you're going to get for this. So you have to just understand the concept, okay? So this will be covered towards the end of the lecture. Now, a population is the entire thing, and sample is a representative sample. This is all repetition, skip. Representative, skip. Okay, so a census is when you don't take a sample. Basically, a census is a count of the entire population. And why do we do this? We want to eliminate the possibility that by chance a randomly selected sample might not be representative of the population. So a census is an example, the only example where people do not take a sample, they just take everyone in the population because they want to find out really specific stuff about like specific variables about the whole population. And they don't want to take the chance of getting a sample which will not be representative of the actual thing, okay? Just know what a census is. They may give you a definition or something. We assume the population under consideration is finite, consists of n subjects or elements. That makes sense. The aim is to make an inference about the characteristics of the population using the information contained in the sample drawn from it. Okay, fine. Study units, okay. So basically, oh yeah, this lecture also contains definitions that you need to know, okay? So what is the study unit or sampling unit? It is the individual elements that we are interested in. For example, if you are conducting a study to determine the average amount of soft drinks consumed each week by teenagers between the ages of 13 and 18, what is the study unit? It is the teenagers, okay? It's not the soft drinks. That's the only caveat to this. Because the individual elements that we are interested in studying is the teenagers, okay? How do I explain this? So the participants of the study basically means the study unit or sampling unit, okay? Okay, so the target population, okay. So there's two things. One is the target population. One is the, where is it? One is the study population, okay? So a target population is the ideal population that you are interested in studying. For example, in this example, you want to study teenagers, all teenagers between the ages of 13 and 18 who are living in Riyadh, okay? Literally all of them, whether they go to school, whether they don't go to school, whatever, okay? All of these. However, you may not always be able to get access to an ideal target population. You know, it's an ideal. You can't really reach up to it practically. So you go with a study population. A study population is a group from which the sample is taken. So a study population in this case is going to be all of teenagers between the ages of 13 to 18 who are currently living in Riyadh and are attending schools. Why attending schools? Because we went to school to sample them. We did not go to people's individual houses and ask them, do you guys have someone who's like, 13 to 18 who, like, we may have missed out on, okay? So it's basically just a concept. Now, sampling frame, the sampling frame is a complete list of all members of the target population. However, such a list is usually unavailable, so we have to use the sampling frame from the study population. Make sense? Okay, so okay, now it says that a random sample, although representative of the population from where it is selected, may not be representative of the target population. Explain. So over here, they mean the same thing. For example, your target population was all of the children in Riyadh. Your study population does not include all of the children. So the sample that you select from this small population or this population that you have may not represent the people that are left out. That's all it means. Make sense? So target population is basically the ideal population, and a complete list of everyone in that is a sampling frame. So sampling frame is basically a list. It's supposed to be from the target population. Practically, we take it from the study population. And this is why, since we're taking it from the study population, our sample that we select may be biased, okay? So what is a selection bias? Now over here, they gave an example of selection bias is a systematic tendency to exclude individual members of the target population. In our example, we are systematically not including the people who do not go to schools. Okay, again. We have a study population. Our example, the study population is the population that we want to conduct, is the population that we want to study, basically, okay? So what do? We take a target population. Now, in ideal situations, you have this target population, you take a sample from this target population, you do experiments on it, whatever you get results, you apply those back, or you infer those back to the target population, and your study is complete, okay? However, practically, you may not have access to every individual in the target population. So you go for a study population. Study population is the people you have access to. So you should be taking a target population. You're taking a study population, which is basically a subset of this. So when you are taking samples from this lesser subset of a population, the sample may not be representative of the larger population that you were ideally supposed to take. Make sense? Okay, if it's not clear, just stop me, it's fine. Okay, so selection bias means that you are systematically excluding people, okay? So the best example to give is a bit inappropriate, but let's say someone is racist, okay? So someone is racist against a particular person, okay? A particular group. For example, if someone is conducting a study, they are biased to select only Al Faisal students. So they will not select students who are not from Al Faisal. This means they have a selection bias. So Al Faisal is their study population. Their target population is supposed to be all people in Riyadh and going to College of Medicine. So they are systematically selecting people who are not representative of the population. Make sense? Our goal is to make sure it's as inclusive as possible and to remove as much bias as possible. Yes, goal of every study is to try to reduce as much bias as possible. You can never eliminate bias because it's always going to be there, but you can at least reduce it. So basically, how do you get rid of selection bias? To include more people, you know, like include the people you are leaving out on, okay? So, okay, what is random selection? This is another definition. So random selection is where each member of the population has an equal chance of being selected. For example, I have a class of students and I want to select them, okay? So the number over here, to select the sample, a random sample, number each member of your population and then select your sample using a random number table or a random number generating process. The opposite of this is haphazardly or arbitrarily selecting the samples on your own. The idea is between this, random and haphazard means, for example, I have a class of students, I number them all from 1 to 10, okay? Now, random sampling would be if I, you know, draw them out. So every name has an equal chance of being selected, or I use a random number generator. As opposed to this, oh my God, can you hear me? Okay, as opposed to this, the second thing is like I just think of numbers at the top of my head and I select them. Why are the numbers that I select not equally as likely to be selected by like someone else? Is because I may have a preference for like number 3, 6, and 9, you know? So if I have a personal preference to some of these numbers, this is why the chances of each number being selected is not equal. That means that this selection of me randomly picking them from the top of my head is going to be haphazard, not random. Make sense? Okay. Sampling error occurs whenever the characteristics of a population estimated from the sample are different, right? Okay, so there are two types of sampling errors. One is a random error. Now, this random error is always there. You can never get rid of it. Why? Because whenever we take a fraction of the study population, just by chance alone, we might draw a sample that is not representative of the source population. For example, we have, let's go to this example. So we have this population over here, okay? We want to randomly select, we want to randomly select things from here. So if we close our eyes or we put a system generator or whatever, and we randomly select things from here, we may select 2 Cs or 3 Cs. You know, it's completely based on chance. If we have 3 Cs, it's not representative of, like, you know, all of them, A, B, C, and D, E, you know, all of them are skipped out. But our method that we used was like not biased, you know? So the method we used was correct. Everything we used was correct, but just by chance alone, we got 2 or 3 Cs. So there's always this chance that you will randomly get something which is not representative. Make sense? Okay, so systematic error is basically it's the same thing I explained over here. Selection bias is an example of a systematic error. Okay, so I am systematically excluding people, one class of people or one group of people. Okay, that means that there is a systematic bias. So how do we get rid of systematic bias? Or it's called the selection bias over here. You randomize, okay? So it tells you how you get rid of it, okay? So bias is also defined as the difference between the value of a statistic we estimate from a sample and the values of actual population parameter be measured or estimated, same thing. Now, 4 types of bias, you need to know the definitions, how to get rid of them. So selection bias, systematic tendency to exclude individual members of a target population. For example, estimated attendance of students registering for BEP. This year, only a sample from the male section. So you don't include the females. You are systematically excluding the females. So you have a problem in your selection process. That means you have a selection bias. How do you get rid of it? You randomize, okay? Systematic versus systemic. Okay, now this is like, okay, just read it through. Systematic means that it's arranged or dealt with consistently according to an organized method. Systemic basically means you have a systemic infection or something. It's a word of biology, not statistics, okay? Next. Systemic infection means that multiple organs are being affected at the same time. Okay. Non-responder bias. Okay, so non-responder bias is basically you had to first you calculate your sample size, okay, and then you knew who your sample size were, like the people in your sample size class. You know that these are the numbers I'm going to go and ask questions on and stuff. Now you give them a questionnaire and they don't fill it out. That means that the sample that you had, you're getting a sample less than that. So that means that you're going to have a non-responder bias because the people did not respond. Okay, so it differs from systemically consistent people because it's not like you're going to a specific, if you're not taking opinions from a specific group of people, it's their own choice, you know? That's why it's different from this. So how do you get rid of this? Is it mentioned anywhere in the slides? I don't know. Let me check my notes. If I wrote anything down. Okay, so you can't get rid of non-respondent bias. There's no way you can do this, okay? Okay, ascertainment bias, okay. So over here, it means that this bias is present when the results of the trial are known by each participant already. So this is classically for randomized clinical trials. For example, I have 2 groups of people. I have to give one of them placebo and I have to give one of them the actual treatment. However, if the people who know they are getting the placebo get the placebo, they may have a psychological effect that they will be like, you know, this medication is not going to work anyway. And due to the psychological effect, they start feeling worse and worse. So this is a bias because they knew they're feeling worse psychologically. It has nothing to do with the placebo. So this is why there is an ascertainment bias. Ascertainment means like you are certain about a result. Non-respondence bias, considered bias because it's the representative sample that you had, it's not the representative sample anymore. There's like 1 or 2 people less than that. That's what it means, yeah. Okay, so how do you minimize this? You blind the patients and the doctors. So it's like a double-blinded study. The doctors don't even know who's getting the treatment. The patients don't either. For the doctors, it does not affect their behavior towards the people. So if they know someone's getting a placebo, they won't be like, okay, you know what? They won't take the measurements or whatever they're doing or treat them the same way as they're treating their treatment group, you know? Recall bias. Now this happens when this usually happens when it's a follow-up study. So for example, you had a study, for example, you taught people how to wash their hands. Then you follow up with this 2 weeks later when you ask them, what did you learn about, you know? So if the amount of time, a lot of time passes between this, you will get some people who will forget what they studied, you know? Yeah, sure, I'll repeat. So you'll forget, the people will forget what happened in the past or what took place in the past. This is why the results you get may have this problem of memory, okay? To obtain this, over here, it says you obtain information from other sources. This is in according to hospital records. For example, in this example, they mean, for example, you're doing a study on patients to ask them, which of you got COVID? Now, it could be that someone got COVID so long ago, not possible these days, but someone got COVID so long ago that they forgot they got COVID, or they don't remember the exact dates of getting COVID. So you go to another source and this. I told you earlier, the example I told you earlier, in instance, washing their hands, and then you do a study later on to ask them what they learned in that study, in the workshop or whatever, about washing hands. The way you minimize that is you reduce the time between follow-up and to the actual intervention. Make sense? How is this a bias? This is a bias because there's only one variable is no longer present. There's another variable of either memory or them not remembering, you know? So all of the variables are not controlled anymore. There is another variable that we did not account for. They just came in. Yeah, memory, or like them not knowing the information. If you're asking them about hospital records, you ask them what was their hemoglobin level, they don't know, you know? So basically the information we get may not be reliable. It may be wrong. Yes, so we were assuming that all of our information would be correct. But now we are not getting all correct information. So when we do the results, we do the statistics later on, our results will not be correct. It won't represent what they were actually supposed to be. So for example, after you calculate everything, your mean was supposed to be 5. You were supposed to make calculations from this mean of 5 and apply it to the whole population. But this mean is actually 6. Does that make sense? So the values that you're collecting or your basic data entry is going to be flawed. What did you ask? How is this about? Oh, what does blinding mean? So blinding basically means you have 2 groups. You are giving one group an active treatment for a disease. The other group has the disease, but you're not giving them an active treatment. You're just giving them something that has no effect. It's called a placebo. So for example, if you're giving someone vitamins and the other person, you just give them empty capsule or something. The idea is the people who are receiving the vitamins or the capsule don't know which one they're getting. Because if they knew they were getting vitamins, that means they already know it's supposed to make me better. So their willpower towards this will be like, you know what, I'm going to get better. The people who already know they're getting a placebo, they'll be like, okay, so not going to have an effect. So why even bother? So they'll be depressed. It will lead to worse results. For doctors, you want to double blind this. Single blind means only patients don't know. Double blind means doctors don't also know as well. When we say it's double blinded, the doctor does not even know if he's giving the other person a placebo or not. Why? Because the doctor, in his mind, he always wants his study to be successful. This is why he may start paying more attention to the people he's giving actual treatment for, if he knows which one they're getting. So for example, I'm giving someone vitamins. I'll check their blood pressure more carefully. I will be friendlier when I'm talking to them. I'll make sure I have time for them versus the placebo people. I'll I'll let someone else do their blood pressure. I won't take the readings twice. I'll just, be pissed off whenever they come because I don't want them to be successful, unconsciously, obviously. That's the idea behind blinding. So if you blind someone, they are not certain about their future. So this knowing or not knowing, the psychological factor does not play a role in the result. Okay. Bias. Okay. So over here, the bias which are not categorized. So good for you. Respondent may not reveal something personal, sensitive, or incriminating. For example, if you ask, do you smoke or not, or how many times have you taken attendance for a classmate, none of you will answer correctly. So this is also a bias. So our goal is always to achieve a minimum bias or minimal bias, because you can never get rid of it, because even if you try to get rid of all of the biases mentioned earlier, you will have non-responder bias, which you cannot get rid of, and you will have random sampling errors. Okay. So you always want to minimize it. Now, usually you can reduce the amount of bias by increasing sample size, but you can only reduce it. You can never make it back to zero. Okay. So now we're going to jump to types of sampling techniques. So there's two main types of sampling techniques. One is called random, and one is called non-random. These all are types of random sampling techniques. In random sampling techniques, every individual in the sample has an equal chance of being selected. Okay. There's an equal chance. Okay. Let's start with non-random first because it's a lot easier. Convenience sampling. What does this mean? For example, I had a study in which I had to go to all second years of Al Faisal. Okay. All second years from College of Medicine. I do convenience sampling. So instead of 100, I know that my sample size is going to be like around 10. So I have to choose 10 people. Now, either I can do a random system, random number generator, number them all from 1 to 100, choose 10 based on the 10 values that I get. Or I can just go to one class, whoever is present in that class, I just go to them and take the results from them. It's non-random because the chances of these people in the class being selected was a lot higher than people who are not in the class, So it's non-random sampling. Now, the thing is, non-random sampling, if you're doing it on purpose, it's like, it's going to cause a lot of bias. So you never do this intentionally. But sometimes you do not have access. For example, if I want to do this study on different schools, sometimes I will not have access to other schools which are really far away and stuff. In that case, you can do convenience sampling, but your study is always going to be considered weaker or whatever, But for non-responder, you just remove those participants and calculate things with your sample. No, you cannot do this. You cannot do this. Non-responder bias, if you remove the number of people, your sample size will reduce. You can't just randomly select 3 more people. Okay, these are gone, let's add 3 more people, because these were not part of your initial sample that you got. If you do this, you are adding another bias to it, or you are, basically you're altering with the results of your sample size, because we can work with a smaller sample. Yes, but so practically, whenever we're doing a study like this, we always account for non-responder bias. So for example, if I do a sample size calculation, my sample size calculation is 250. When I'm doing an initial survey of people, I'll make sure to send it to 275 people, because I know around 10% of them, or around 25 in this case, will not answer. You can do something like this, but you cannot change the 250 number. If you get 249, that means your sample size is smaller. That means the chances of your experiment not being statistically valid is lesser. Remember Khalid's lecture? Reduce sample size, more chance of one of the errors, alpha or beta. Yeah, we cannot get rid of non-respondent bias once you have it. To prevent it in the beginning, you think, for example, you need a sample size of 250 students. But when you're doing the 250 students in the beginning, you do 275 because you know some of them are going to leave or some of them are not going to respond. Does that make sense? But after you have selected these students, you can't choose, oh, I need 3 more, let's check 3 more randomly. Three participants don't respond, the initial sample size. Okay, let me explain something to you. Usually, once you have a population, right? The way you calculate sample size is, this is out of this lecture, but it's just like to give you guys the concept. Whenever you're doing a study, for example, I am doing a study on a school, okay? Or I did a study on a school. We first estimate the population size that we have, the total population, or our target population, okay? Then we take the study population from that, right? Then we go to a sample size calculator and we calculate the sample size needed for us to get a statistically significant result once we are done with all of our calculations. So we have this predetermined number in our minds before we start the experiment, okay? Now, once we have that number that we need, we can't go below this. Okay, why do we take this number in the first place? We take this number for 2 reasons. One, because we want to save time, and secondly, we want to save resources, okay? So we take the minimum number of people that we need to make our study statistically significant, okay, or make our results valid. So we take a sample size. For example, I'm taking 250 students. Now, initially, what I can do is, since I know there's going to be a non-responder bias, I will select 275 students. And out of those, 25 will not respond. So I have the minimum 250 student sample size that I needed for my study to be significant or relevant in the publishing world, okay? For example, I got a sample size and, instead of 25 people, 27 people did not respond. That means that my sample size, which was supposed to be 250, is now 248. You cannot remove outliers. If you remove outliers, that means you are tampering with the data. You cannot tamper with the data. So if you have 248 students instead of 250, that means your sample size is not as big as you needed it to be. So your chances of making conclusions which are not statistically significant are larger. You can't remove outliers. Otherwise, there's no point of the study. 3 participants don't respond. Initial sample size was like 500. Yeah, so this is what I mean. Your initial sample size is the target that you need. Initial sample size is 500. So you will target 550 because you know some of the students won't respond. However, once people have not responded, once you get to 490 instead of 500, then you have a non-responder bias. Then you can't get rid of it. Just like, yeah. So the idea is you can, if you take more participants in the beginning, you can try to not get a non-response bias. Once you have already selected people and they don't reply, then you're stuck. Then you have to, then what do you do in the paper itself when you're publishing? You just declare it. So you declare our sample size, the ideal sample size is supposed to be 250. However, we got 245 because 5 people did not respond. As long as you mention it, the study will be considered and will be, nobody can make a mistake out of your study. But if you fail to mention it and somebody points it out to you, that means you made an error in all of your calculations, okay? So you just have to take that into account. Okay, so now let's talk about the 4 types of random sampling, okay? So simple random sampling is the most basic probability, and units are independent and randomly selected. Units means like individuals, okay, from the sample, off the sample. Without replacement, that means if you select someone, you can't like put him back and select him again. Each study unit has an equal chance of being selected with a probability of n over m. So this basically means if I have a sample size of 10, and my initial population is 100, that means that the chance of every person being selected is 0.1. So there's nothing to this because n is the sample size and big N is the population size, okay? So simple random sampling minimizes the possibility of bias because everyone has an equal chance of being selected, okay? So another example of this is, where are you? Over here. So over here, we can literally choose anyone from the sample. There's no order to it, nothing, okay? This is a simple random sampling. Does this picture make sense? And basically, you're not repeating whoever you select. The way you're selecting is going to be the same thing, number generator or something, not from the top of your head. Is this clear? Perfect. Okay, so one way is to list them, the other way is to use a computer, whatever. This is an example. Okay, so systemic sampling. So systemic sampling, it uses a pattern for selecting a sample instead of selecting the numbers from there. For example, you select every 5th item. So in this case, what we do is, this is another method of random sampling. What we do is, okay, let's work with an example. It's a lot easier to understand. So for example, we have a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, we have a total population of 12 individuals. We need a sample size of 4. Okay, so what we do is, let's go back to this. What we do is, an initial sampling unit is randomly selected from the first k units on the list, which is called the sampling interval. What is the k? It's the number of every student that we'll take. How do you find this? You divide 12 by 4, which is equal to 3. So this tells you that you have to select every 3rd individual, okay? This is what k is. Now, if it's not an integer, you round it to the nearest whole number, okay? Now, k is the term we're going to take. So we're going to take every 3rd individual in our selection process, okay? The second thing we are going to do is, the initial number that we take has to be either 3 or less than 3, okay? So there's 2 things in this. One is k, the value of k, which is going to be your sampling interval, which is going to be every 3rd individual you're going to select. So in this example, we're going to select every 3rd individual, okay? So there's a difference of 3 between these. There's a difference of 3 between these. The difference, the other thing is, the other point is that your first sample that you select cannot be the number 4 because your k was 3. If it's number 4, that means the people that you will select every 3rd person will be 1, 2, 3 instead of 4. You needed 4. Does that make sense? I explained it in a really roundabout way, but does that make sense? So for systematic sampling, what you have to do is, number 1, you have to calculate the k. The k is supposed to be capital N over small n. What we do is, there we go, this is a good example. So what we do is, we have k, which is supposed to be big N over small n. Then we generate a random number as our first term between 1 and k. For example, it's 6 over here. So starting with the 6th person, we will be selecting every 10th person. So this is the value of k, and our first value is anything less than k, because it's going to be the first number we select. Make sense? What happens if we start selecting from, instead of from 1 to 10, we select from 11? We will select 11, then we select 22, then we select 33, then 44, okay? Yeah, okay, 44, and then all the way to 99. What happens? This original 10 people or 11 people before this, nobody was selected from this. So instead of getting the sample size, we get sample size n minus 1. We get 1 less. This is why the first value we take is supposed to be less than our interval. Yes, we can select any random number, provided that is less than k. because over here we just have like this one number that we randomly selected, but we're going to follow the same pattern. So every term, like every other term is going to be with the same interval, sampling interval. Okay, so over here they give an example. Suppose a hospital wants you to study the population's habits. The sample size they want is 30 students. Using sampling, systematic sampling, they want you to choose every 15 until they reach 30 patients. So they need to take a total of 30 people, and they want you to take every 15th person. Okay, show your work. They give you the sample size, they give you the population size, you divide them, it's going to be 15. So then you generate a random number. Your question, we can generate any, but you don't choose on your own. You'd still generate a random number. It's not like I'm choosing on my own, it's 1 or 3 or 5. You choose 11, and then choose every 15th patient after the random point of 11, okay? So Bushra, your answer is you have to still generate a random number. You can't choose on your own. Choose a systematic sample of 8 students from a class of 80, okay? So this example, I would prefer if you guys practice on your own time, because although the theory looks really nice, but sometimes people can make mistakes once they're doing it for the first time in the exam. So just practice it once, That's about it. Okay, so the good thing about this is that it's easier to apply than simple random sampling. So in simple random, you basically just have a electronic generator, and you generate the list. Over here, it's easier to apply because you don't have to do that, okay? Over here, you only select one single random sample, and then it's even distributed over the entire population. It only works if this list is randomly ordered. The list itself that you are selecting people based off, it should not have for example, if you are calculating GPA of students or something, or if you want to know GPA of students, you can't have them ordered from least to greatest or something like this. It has to be completely random. There is a danger that the chosen interval may conceal a pattern of periodic sampling. Okay, so this is the only danger that you have in if you have in systematic sampling. How does that work? For example, if you have this example over here, right? It may be possible that these 2 students have a particular characteristics which all other students don't have. If you are selecting people and your K value is it does not result in you selecting these 2 students which are different from the rest of the people, then your sample that you selected will not be representative of the total population. But there's only a slight chance of this happening, provided that there's a trend that is so small that is present in these individuals that are not included into your sample size. Does that make sense? Hello. Yes or no would be nice. Okay, so basically, if your K value is larger than the pockets of people who have a special trend somewhere, then you may have this chance of bias, okay? Okay, for example, a particular subgroup of the target population may not be represented in a given sample purely by chance, okay? So we might not choose any of the 17 due chance, okay, same thing. Okay, so now basically we've covered 2 types of sampling. One is simple random sampling, where you just generate a number. The second one is where you generate an order and then you stick to that order, which is known as systematic, okay? The third type is stratified sample. And this example demonstrates really well how it can be seen. So stratified basically means that you are dividing the people according to a certain class. Stratified literally means layers. So you have layers of people who are separated into different categories, okay? So for example, over here you have these categories of people. What you do is you stratify them, divide them into different categories, and then you proportionately select individuals based on their number in the actual population. Select any number, yes, oh, got it, randomly. By randomly, if you mean that you select them using a random generator, yes. If you mean that you select them using the top of your head, no. Okay, so basically you have this population. So you have different colors, okay? So you have this color, and this is 40% of the actual population. You want to get a representative sample. So what you do is you take a proportional number, you take, since it's 40%, you take only 4 individuals. If it's 30%, you only take 3 individuals because you want it to be representative of this sample, of the population. You know, you want to be representative of the population. So you first divided them into different categories. Then you proportionately selected them according to their numbers in the actual population. Okay? So that's basically stratified. Now the thing is, the reason you're studying this is because in different types of studies, you will have to like determine which type of sampling you're doing. So none of these sampling is like best and none of these are worst. These are just different types. Some have their advantages, some have their disadvantages. But you can't like really say, okay, this one is the best out there, you know, because it depends on the type of studies. So for example, over here, it says, over here, okay. The idea is, the condition for this is that they should be mutually exclusive. What does this mean? This means that no person is repeated in the same category. So over here in our example, this person is not repeated over here, you know, and the other one is exhaustive. Exhaustive means that every individual should fit into at least one category. You cannot have one individual who does not fit into any category. If both of these two conditions are present, they are exhaustive, all the members are exhaustive, and it's mutually exclusive, no one is repeated, then only you can stratify them into different groups. Otherwise, this method cannot work. Yes, for example, adults, children, and elderly, yes. Yes, and then we can track them. Yes, exactly. So divide the population into subgroups or strata, ensures that each stratum is representative in the overall sample, okay? It does not require any study units. Okay, so over here, it's different from simple random sampling because it does not require that every individual has an equal chance of being selected, but based on their population numbers, they will have a proportionate chance of being selected, so it still makes sense. Why does it say, why do we do this? Certain small groups, for example, elderly, may have to be overly sampled because you want a more in-depth analysis, or their numbers may be more in the population itself, you know? Okay, so the good thing about this is you have a smaller variance if you use this method, because you are dividing them into specific sample sizes, okay? So your variance is less, which means the study is more precise. Okay. This is one benefit as compared to a simple random sampling. So if you have the option of stratified sampling versus this simple random sampling, and all of you can divide them into different categories. You want to study the different categories. All of your members are mutually exclusive. All of them are exhaustive. You can use this for a better, more precise result. Make sense? Okay, so now cluster sampling. Now cluster sampling is once you divide the sample into different groups, and then you sample them. For example, you divide them according to like different clinics, so people present in different clinics, different families, different classes, and different hospitals. Now, there's 2 types of cluster sampling. One is that you have like this population, and then you take clusters from this. For example, you take individual hospitals from this, right? So you have a list of all the hospitals, and then you take all of the, like you investigate all of the individuals in these different hospitals that you randomly selected. If we go over here, now over here you have this population of medical students all over America, okay? Then what you do is you divide them into different colleges, okay? Different medical schools. Then you choose, like you randomly choose the number of medical schools you need, okay? So for example, you choose these 3 medical schools. Now you have 2 options. Either you can study all of the students in these 3 schools, or you can randomly select students from this further, okay? If you study all of these individuals in the school, this is known as one-step clustering or one-stage clustering. Randomly select a sample of groups or clusters and investigate all the study units within these clusters. Secondly, the second thing you can do is randomly select clusters, and then within this, you randomly select a group of participants. Now, this depends on your study and the number of participants you actually need and all of this. It's more to do with your specific study in mind. So basically just categorizing so we can study track the differences. Okay. So if something is more location-based, like an outbreak in a hospital, doing a cluster sample would help factor in. Yes. So in the beginning, the hospitals you selected were random. This was the random sampling that you did. So you like made the list, generated the list from the computer, and then you selected these 3. Now, out of these 3, you have an option of randomly selecting participants from here as well, or studying all of the participants. So in a cluster, one thing is that they have something that like the people inside that cluster have something in common. Either they're going to the same hospital, or they have their same family members or something, you know? So they have some commonality. And secondly, they represent the population. So it's not that these, for example, this is an immigrant family that was not present anywhere else. You can't do it like that. So these are the 2 conditions. Honestly, this was not mentioned in the lecture, so you don't need to know this. It's just for understanding, because you're going to use these techniques throughout your life. It's more to do with like actual life than your exams, provided you go into research or like you do some sort of research in your life. So the advantages of this is it's more economical because you choose less number of people, or you choose specific hospitals, and then you only have to go to these hospitals, you know? So you randomly chose 3 hospitals. You only go to these hospitals instead of going like all over the country and picking 2 or 3 people from each hospital. The disadvantage is that your variance may be higher or less precise than this. But honestly, when you have the choice of economic study versus a slightly larger variance, obviously you'll be going for economic, you know? So it just has its advantage and disadvantage. Okay, so now we have a practice quiz, same question. What do you guys think? I will give you a hint. Thank you. Cluster, okay? So the answer is clustering. In simple clustering, we are dividing the population of interest into subunits, such as families. Random sample of these is used. In simple random sampling, it's not a group that is selected, it's an individual. In stratifieds, first we stratify them into different groups such as age and gender. See, these groups are supposed to be exhaustive and mutually independent. Now, in systematic sampling is ordered by characteristics such as age from starting point and then randomly chosen, and then the remainder of the sample is collected by a predetermined scheme, which is basically the K value, okay? In convenience sampling, this is convenience sampling. This is the sampling which is non-random, okay? Over here, they just selected the first 30 numbers of the people that had the disease, or they just go for the, over here is another example. So the sample is an easy to reach or contact a group of people. For example, you just go people standing near to the festival food court instead of going into all of the different students, okay? So that's non-random. It is, the probability is not equal of selecting everyone is not equal, so it is unknown. In random sampling, you always know what the probability is because it's going to be capital N small n over capital N. That's going to be the probability of everyone in a random sample. Over here, it's unknown. Are prone to bias, obviously, and cannot be assumed to be representative of the total population. This is basically just an example, and that covers this lecture. Now, do you have any questions about this lecture? This lecture honestly does not have a lot. It just takes some time to understand the different sampling methods. Once you get that, it's really easy. This is another example of clusters. So basically, this was a family. This was a family, and then we chose this family, and then we chose everyone in that family. You know, we did not randomly select further. So this is one stage. This is also one stage. Okay. Question mark. What's the question mark about? Okay, sure. Okay, so we're done with this lecture. Now, the other lectures I can probably finish. Oh my God, it took an hour. Sorry, I apologize. I thought we'd be done with all of the lectures in 1 hour. Now, the rest of the 3, I can probably, inshallah, finish them in another 20 minutes max. Do you want to continue? Okay, so this is rates. I think you already took this lecture because honestly, this was like probably the 3rd or 4th lecture we took. But if you have not, know what demographics are. Demographics basically concern, demo means people and graphics means numbers. So basically numbers related to people, okay? Vital statistics are basically used to describe the life of a population. So it includes stuff like births, deaths, marriages, occurrences of disease. You just need to know the definition. And you need to know that vital statistics are used to make analysis or spot results in something. Excuse me for a second, please. Okay, that was my parents. Those were my parents asking if I'm still alive. Okay, so it's used to make comparisons among groups, okay? What else? If you just get a raw number, it's called the raw number. So for example, you get the number of deaths in USA in this time. This is a raw number because, why is it raw number? Because we haven't done anything to this. We haven't done any calculation on this, or yeah, I think that's it. And these are more difficult to interpret, and I'll show you why. So you need to know vital statistics are used for these 4 things that characterize the population. Spot trends is most probably going to be an MCQ, so just memorize all of these, or at least know to differentiate which one is not included. Make comparison among groups. Okay, so the reason why you don't really use raw numbers is because of this. So basically, why were the death rates in 1991 this, and why were they increased in 1992? So it could be for a number of reasons. It could be that the total population you had was less, so that's why you have fewer deaths. Or it could be that they had some sort of disease and there were more deaths in 1992. So basically, we can't really make any generalizations or any conclusions from raw data. Okay, now you have different types of ways to measure the disease burden, okay? So count is simply you measure the number of people in that group or affected by the disease or in that population. Now the ratio is basically you are dividing one thing by another, one value by another. The denominator is not related to time. That's number 1. The second thing is numerator and denominator may not be related. The perfect example of this ratio type of thing is odds ratio, because the numerator and the denominator were not related to each other, as in they weren't inclusive of each other, okay? Proportion, we already covered this. So proportion is basically numerator, which includes the denominator. Type of ratio, part of the denominator, health outcome is relative to the size of the group. It's not time framed again, and it has no units. So why does proportion have no units? Because units over at the top and the bottom will be same, so they'll be canceled out. But may be expressed as a percentage because they are proportion of each other. Okay, percentage literally multiply proportion by 100. Okay, rates. Now, rates are basically the same thing as ratios. They are similar to ratios because you have a numerator and you have a denominator which may or may not be related to the numerator. However, in the denominator, it gives you a period of time. For example, whenever we use rate, we think of death rate. So for example, or birth rate, whatever, differs from the proportion because the denominator involves a measure of time. So we can't call it a proportion. It's a type of ratio. So number of events that occur in that given number of time. So whenever we say death rate, we always say death that occurred in this time period, in 1 year or something. So rates is always related to time. So rates versus proportions can be used interchangeably or are used, but they are not the same. Read the definition, have no units of time, incorporates units of measurements and are dependent upon measure of time. Okay, so basically everything I said. Like, yes, probability is always proportion. Nice. Or relative risk, or risk. Oh my God, yeah, I'm not going over this. Okay, so mortality rate basically, okay. Now, a death rate or mortality rate is the number of deaths that occur during some time period. So basically, some time period, okay, and it's divided by the total population at risk during that time period. So basically, in the death rate, the numerator is part of the denominator, right? Now, sometimes to make it easier for us, we want to get rid of the decimal places. So instead of saying the total population, we just multiply that by a certain number and we say it is per 100 or 1,000 live births, okay? So we just sometimes use this to get rid of the decimal places to make it easier for us to understand. For example, we go like the death rate in this year was this much per 1,000 population, which means per 1,000 population, number of deaths among the population that was in that year, you know, so the population in 1991. So he basically says if you compare the death rates, this is no longer a raw measurement. You have done something on this. It's not a crude value anymore. So you notice that actually a number of people died in 1992. So the death rate decreased. What? Although a larger number of people died, the death rate increased because the actual population increased, okay? Now, infant mortality rate, this is the only one that I wanted to highlight. Infant mortality rate. In this, the numerator is not part of the denominator. It's the number of deaths during infants of their first year of their life, okay? Divided by the total number of live births during that year. So the time frame is equal, but the denominator has total number of live births. Numerator has deaths. So can we call this a proportion? No, we cannot. Can we call this a ratio? Yes, we can. Can we call this a rate? Yes, because it includes time. So rate and ratio are somewhat related. Okay, and it's really important to be safe. Memorize Ethiopia, memorize Sweden, and memorize Saudi Arabia. Just to be safe. I'm sure there won't be a question, but just to be on the safe side. And I'll tell you why in a minute. Okay, so accrued rate is a single number computed oh my God, what does it say? Computed as a summary measure for entire population. So all of these numbers have been crude. If you go for specific rates, it's within well-defined subgroups. So for example, if they are separated by age, race, gender, and other population, we would no longer call this crude, and we will call this specific. So now there's two things that we learned. One is raw data. Raw data is that we don't do anything to it. Crude rate means that it includes the entire population without making any specific subgroups. Specific rates means that we have divided them or stratified them into different categories, and then we are basically checking rates among them. Make sense? And this is an example of specifics. Crude and raw are not related to each other. Raw is basically this number of deaths in 1 year. Okay, raw is basically number of deaths in a particular year. Okay, crude is basically all of these when they are considering the whole population as a whole. They're not dividing them into different categories. Okay, so a raw data can be a crude data because raw is just a number, it's a count. Crude data is concerned with the whole population, or like population stratified into groups. By difference, I mean just know if there's a definition of a crude data, like know the difference between definition of crude data and raw data. Make sense? And that's basically we're done. Okay, this is like one of the simplest lectures out there. If you make a mistake in this, after you have finished risk ratio and odds ratio, I will beat you. No. Let's go to the 5th one. Basic concepts. Okay. So over here, you need to know what these mean. Know the definition. Epidemos, logo, study of people upon them. Okay. Know this definition. There's always an MCQ on this. I'm pretty sure you had one in the midterms. Specific rates are basically, they're divided into different subgroups. So for example, they're either divided into age, or they are divided into, they are divided by age, or they are divided by gender, or they are divided by any other category. So basically stratified. Okay, intervention. So intervention, basically whenever you're doing an experiment, intervention is the treatment or the change that you bring into the experiment. For example, if I want to see results of a vaccination or something, the vaccination is going to be the treatment, so that's going to be the intervention. If you're doing a workshop on a school, your workshop is going to be the intervention. So whatever you are intervening with is basically the intervention. So it could be social activities like an educational program, could be lifestyle changes, whatever. Okay. Hypothesis, it's just a definition. So it's basically the explanation that you want to prove correct or wrong by using statistics, right? Theory provisionally accepted in order to interpret certain events or phenomena to provide guidance. Just the definition, nothing to be done. Okay. Living in 2020, you better know the difference between these. Pandemic, entire worldwide. Endemic, it usually occurs in a region. So for example, malaria is a bad example. For example, flu is endemic to Saudi Arabia because the amount of flu is always like around 50 or 60. You know, it's a random number I just made myself. So it's endemic. It usually happens, or it like varies with time. Sometimes it happens, sometimes it does not happen. But if there is a disease which occurs clearly above the normal expectancy in a group, this is called an epidemic. But this is going to be in one region only, like in Saudi Arabia. Epidemic in worldwide is pandemic, which is COVID-19 these days. Okay. Any confusion about this? Okay. So moving on, application of epidemiology. So over here, it's the idea that a clinician cares about one individual only, whereas an epidemiologist is concerned about the community, blah, blah, blah. He always takes the wider picture into account, all of this. Okay? There we go. Health of individual is clinician, and health of community is epidemiologist. Yeah. we memorized these numbers, but we didn't have COVID-19, so I don't think there'll be a question on you. Okay, so this is basically the only important topic in this lecture, which is primary prevention, secondary prevention, and tertiary prevention. So what's going to happen is there's going to give you a scenario, and they're going to ask you, okay, is it primary, tertiary, secondary, or some other random example, some other thing that's not the answer. So what is primary prevention? Primary prevention is when you prevent a disease or injury before it occurs. An example of this is immunization or education or health legislation. So you prevent basically the risk factors of something happening. Okay. For example, so focus on eliminating the risk factors. Okay. Then you have secondary. Now secondary, there's going to be two words, either testing or screening. Usually it's going to be regarding this. So either you prevent the disease from occurring in its early stages, or you reduce a complication of a disease that has already occurred. So how would you think of this? It's basically going to be screening tests. Now this example, it's really shady, okay? I don't get why they put this over here, to prevent further heart attack or strokes, because this could also be interpreted as tertiary intervention. So just memorize this one. I don't know why they put it here. But usually they focus on early detection and early treatment. So acute treatment, whenever we have acute management of a disease, it's usually going to be secondary. Okay, and tertiary is always going to be either you rehabilitate patients or you prevent serious long-term complications, okay? Or you improve their quality of life. So, okay, I actually got the difference, what they mean. So over here, you see chronic disease management, long-term diseases, it's going to be tertiary. Over here, support groups is to, further increase their health later on, improve quality of life, is going to be tertiary. Physical therapy for stroke patients to improve their quality of life. Over here, the reason why they chose this as secondary is to prevent further strokes or heart attacks. So they are preventing the same disease from occurring again. If this was preventing complications, we would have said tertiary. Okay, this is the difference. Not screening after cancer treatment. No, screening, we want to detect if the person got a random population, normal individuals got cancer. So for example, for prostate cancer, they have PSA levels. So randomly, anybody who is above 50 who comes to primary clinic, they just screen them for it. They check PSA levels. If PSA levels are higher than a certain value, they're like, ooh, this person may have prostate cancer, so they do further tests on them. When they do further tests, they figure out if he has it or not. So the idea is if the person had prostate cancer, we catch it in the earlier staging before they actually start to develop symptoms and it becomes more dangerous. I'm asking for tertiary. If you are saying screen for recurrence, then maybe. Because you want to further. Actually, screening for recurrence, I would probably put it into secondary because. Or tertiary. Good question, honestly. Could be either, I guess. Recurrence. Good question. Let me think over it. Okay, so until then, to practice on this, okay? So birth control, what do you think? Primary, secondary, or tertiary? It's probably similar to heart attack, you're right. It's probably similar to heart attack. Yeah, okay, let's call it secondary. This one, promote birth control use. Okay, so they would never give you this example, but it's over here in this example, it's taken as primary. Why? Because in this specific example, we are making people who are highly susceptible to develop like we're taking individuals, for example, we are taking cousins who are married together. So they are highly susceptible to having children who have congenital abnormalities. So they use birth control to prevent this from happening. So this is prevention, it's going to be primary, okay? Okay, administer chemotherapy. Primary, secondary, or tertiary? Okay, so chemotherapy, they'll never give you this example either. But chemotherapy, in the video that I was watching where they give this example, chemotherapy is basically to prevent complications. So it's going to be tertiary, but it could be interpreted as secondary as well. They're not going to give you such complex examples, but I just want you to get the concept. Yeah, so secondary basically focuses on early detection and treatment. Tertiary focuses on improving the quality of life. It basically focuses on reducing complications, these two things. Or reducing disability or complications. For example, if a person has diabetes, okay? If a person has diabetes, you know, or you will study that a person who has diabetes can have long-term consequences of blindness or diabetic foot or something. So if you do screening on them, you are preventing further complications. So that's going to be tertiary. But if you are treating the diabetes itself by giving them insulin, then that's going to be secondary. If you are screening for diabetes in a person who does not have diabetes at all, that's primary. Make sense? I think diabetes is like the easiest example to make sense out of. So by managing the long-term complications, I mean they regularly, whenever they come to you in the clinic, you always do an eye test on them. You always check their feet to see if they have any ulcers or not. This is what I mean by preventing complications. So if you have a vaccination clinic, flu vaccination clinic, what is that? Yes, primary, because you are preventing vaccination. Passing, texting while driving legislations. Anything that has to do with legislation is going to be primary. Okay, now this is interesting. Provide a free COVID or HIV testing. What is this? Okay, so this is primary because this is similar to screening. If a person has symptoms and then he comes to you and then you test for it, that means it's secondary. Over here, you are providing free HIV testing to anyone who wants it. Same thing as the COVID-19 tests we have on the app these days. Any random person who thinks he might have the disease, even without symptoms, just goes there randomly and says, please test me. So they're primary prevention. Because if this person, they want to catch the person before he develops a symptomatic stage of the disease or a worse stage of the disease. So before the symptoms occur, if you're not coughing or anything, they'll still test you to pick you out and isolate you earlier to prevent further spread of this disease. Okay, now secondly, the other important concept in this is the idea of self-immunity and herd immunity. Now, I'm pretty sure you all have a good idea of herd immunity right now because of the situation these days. But individual immunity means that I myself am immune to MMR because I got the vaccination, okay? Individual immunity means that I have 5 people in my family, okay? 2 of them are vaccinated, okay? For example, my parents are vaccinated. The 3 children are not vaccinated, okay? Now, if one of these 3 children gets the disease, they cannot spread it to 4 other people because 2 people are already vaccinated. They can only spread it to the 2 people who are not vaccinated. That means that it becomes more challenging for a disease to spread because there are few susceptible people left to infect it. So the idea of herd community in the beginning when COVID pandemic struck was that, you know what, in case we do not develop a vaccine, a certain amount of people will get COVID, they will become immune to it because they got it and recovered. And then basically if someone else gets COVID, they won't be able to infect this person because he was already naturally immunized against it. Because he got the illness himself earlier and he's naturally immune to it. The problem was that we could not wait so long as for it to naturally start having herd immunity. That's why they're like in a hurry to develop vaccines and stuff, because we want to artificially give people herd immunity. This is basically the concepts on which vaccinations work. For example, the most famous example these days, or like even 20 years ago, is the idea of getting rid of smallpox in the world. What they did was they vaccinated almost everybody in the world. So now if anybody even has smallpox, they can't give it to someone else because the chances of that other person is highly, highly, highly likely to be vaccinated or to be immune to this. This is why we claim now that we have gotten rid of smallpox from the world. And polio is like almost close to it, except for like a few regions in the world. So for polio, there's a really good herd immunity, but we can't say we eradicated it completely, okay? So when a large number of population becomes immune to COVID-19, the spread of virus slows down. Almost 80 to 95% of the population must be immune. Yeah, so this is a problem. A large number of people, almost 85 to 95 number of people must be immune to it to stop the spread, which is not gonna happen anytime soon. Main objective is to slow down, prevent the spread of the infectious disease. Okay, this value right here, memorize at least 34 million or at least 34.9 million. Because we had an MCQ, random MCQ, we just asked total population of Saudi Arabia, and we were just like, so yeah, and we are done with this. Any questions about this? Yeah, that's a bad idea to wait so long. But the idea is eventually, if we do nothing, eventually we will get a herd immunity against COVID as well. Which number was this? Basic concept. Okay, now we're moving on to our last lecture. Okay, 20 minutes, 3 lectures. Not bad. Last is this lecture. I don't have to explain anything to you guys in this lecture, because if you go to presenter's notes, it's literally a course that someone got, and they literally everything about it, it's mentioned in the notes. You just have to read this. Now, cervical cancer treatment. Treatment is secondary. Screening for cervical cancer using pap smears is going to be primary. Okay, so the most important thing about this lecture is that a lot of students from my batch, they skipped this lecture because there was like, everything is repeated from the other lectures. However, you see these blanks, you see these examples, you see these MCQs, they came copy-paste in our exam. We had 6 or 7 of these. So imagine a person reading through these, memorizing the answers, versus a person who did not even touch this lecture. They easily lost their A. In my batch, I remember the amount of failures for BEPs was the highest. And I don't know why. I took it down to people not doing this lecture, which is like easy 7, 8 answers. And the second thing was people not having time and wasting their time on the correlation coefficient example when it's just for 1 mark. You can just wing it. Some people, like, they literally winged it and they got the correct answer. Okay, so you need to know, like, what is the difference between descriptive and analytic study. Basically, anything you have questions on, just memorize. There's nothing to explain in this. Wait, just let me go through the slides once, if there's any concept left. Okay, so you need to know what is a host, what is vector, what is transmission. This is, I think, the only thing we didn't cover. Determinant, distribution, you'll get this once you read this. Nothing to explain, honestly. And this is just read it. Read this again. Okay, so observational study is basically a cross-section study wherever you give out questionnaires. Experimental study is where you have a treatment group, where you have a group that was exposed, for example, in cohort studies, or example in case-controlled studies. Okay, so observational is usually going to be your cross-section studies, or your, basically in which you try to find the prevalence of something. For example, prevalence of people who smoke in Al Faisal University. Just, you're not doing anything to the results, you're just describing the stuff. So it's also observational and it's also descriptive. This is good for your own knowledge, nothing to do with the exam, memorize. Okay, cross-section studies, I explained this. Cohorts, case control, I already covered this. What else? Memorize, honestly. They explain all of this in the previous slides. Okay, and lastly, I added these two slides, which is basically the other one. Okay, now, do you have any question about the exam itself or about any of the topics that I covered right now, until now? Anything you're not clear about? Anything you want me to repeat? Anything at all? Not Khalid's lectures, because I don't revise those, but other than that. I will take that as a no. Now, I have a few questions. Alhamdulillah, everything's clear. Firstly, when is your exam? You still don't know? Okay, when's your POD? You have POD? When's your POD final? Okay, I don't know what you guys mean by voting link, but as far as I know, all of College of Medicine exams have been finalized. Their dates have been finalized. So please confirm with whoever if this is correct or not. Yeah, okay, just confirm with your BLC or ask him or her to confirm with assessment office. Wow, that's amazing, because we tried to change our parallel, and for fourth years, there was like, no way we are going to do anything for you guys. Okay, so your final is going to be on the 27th. How many days do you have? You have a good number of days until POD consumes you guys. Okay, so the way I would suggest is if your exam is going to be, BEP exam is going to be after your final, what I would suggest is, since you guys already spent hours listening to Khalid and listening to me, thank you so much for listening firstly. Since you guys spent a lot of time understanding the concepts, I would suggest that you guys either quickly go through the slides, since everything is fresh in your minds, within like the next 2 days, or you use the slides and my concepts. The thing is, my concepts, like, they summarize everything. So the way I studied for it was, basically, I made these notes. Then same thing, Khalid gave me this crash course. Everything that was unclear to me, I added to my notes after listening to his crash course. Then, since, like, everything was fresh in my mind, I revised all the slides in 2 days. And then I let go of BEP. Then the last 2 days after the 27th, when you're done with this, you have 2 days, right? Over there, either you solve the questions right after this. Yeah, okay, I'll tell you what to do. Right now, what you should do, or what I advise you to do, is personal advice. You don't have to take it if you don't want to. I would advise you, since you have already learned all the material by me and Khalid, if you have attended both of them, try to solve previous batch questions. You don't have to solve all of them, just solve 1 or 2 batches, okay? The final. This will give you an idea of how much retention you have. Then in the next 2 days, you spend revising all of BEP slides, okay? Just go through them. If anything is unclear, you go back to the recording, listen to that specific part of the recording until it's clear, okay? Your concepts are clear, everything is clear, then you forget about BEP, focus on POD, because POD is it's 5 credit hours. It's like one of the most difficult exams you're going to have throughout your medical school, and it's honestly scary. Get rid of BEP, get it out of the way, get your concepts cleared out. The last 2 days, what you will do is you will do all the remaining previous batch questions. Any previous batch questions you want to revise. If you do my notes once now, you'll be familiar with them. So once you revise them, you can literally use my notes to revise everything within a day or 2. And anything that's not mentioned in my notes, or like it's new for you guys, you just go to those slides specifically, or any of the lecture slides in Khalid's lecture, which like you think you want to revise, you just go over them in the last 2 days, and then you give the exam. This is my advice. This, I think, would be really good for you guys. I don't know what you guys think. Please let me know if you guys agree or not. What else? Okay, so now let me show you the thing I have. These are my notes. This is basically README. It tells you This is my concepts. Don't worry about this. This is fourth year stuff. README. Okay. So README basically tells you the list of lectures that we had. It tells you where relative risk and odds ratio was. And it gives you the link for this, and it gives you the link for this. I have already sent this to Ijaz because he's the head of PAL. I don't know how much involved he is in this or not. Now, my notes are like this. I don't know how useful they're going to be to you. Basically, everything from the first lecture to the last lecture, I kept on writing. So I don't know how you want to use this. I don't know if this writing is legible to you guys or not, but basically it includes everything it's summarized. So it includes all the important points. I solved the previous batch once, and then I added anything that I thought was really useful that I had to add in this. I personally think it's pretty good, but then again, I was only using it for myself. I wasn't using it for other people, and I didn't give it to other people earlier. I just thought it may be useful for you guys. If it's not useful, if you have another way of studying, honestly, go with it. I don't mind at all, okay? So it has all of Khalid's lectures, whatever information he said, I mentioned it as well, but this was 2 years ago. What else do I have to tell you? Yeah. Now, this last slide that I made, do you guys need this or no? This random one that I just made. Can you please send the link for the sampling methods video you used? I don't remember. This is from Google. These are from Google's, the sampling methods. These are from Google. This is from a video, but this was like a random video. And when I watched the whole video, it was 10 minutes and it was not even useful. So just don't go for this. I can give you, same for this. I got it off a YouTube video, but I don't want to share it because these examples are not relevant to you. This was just for practice. I can share this if you want with the answers and the presenter notes. The only useful video that I think is useful to you is this video, which I included in the description of the first lecture. So if you guys want these slides and this particular link, I can send it to you. If you don't, khalas, it's up to you. I don't mind either way. David, do you guys have any other questions? Anything else you want? Okay, lastly, I need feedback on how I taught you guys because this is the first lecture I gave on Zoom for such a long time. So you can email me the feedback if you guys want, please. I really appreciate that. On tips on how to improve. What else? Yeah, that's all I need. And as Khalid said, prayers are really, really important. So please pray for my exam. The upcoming exam is surgery and it's not easy. If you have any questions, you guys, I think G&D can share my number with you. But honestly, I would prefer if you email me because I'm being spammed by a lot of different people and I tend to ignore people while I'm studying. So I would prefer if you email me. If you want my email, I'll send it to you here. If you have any questions regarding the pre-midterm lectures, you can also ask me. You know how Khalid was busy? I can probably answer you. Inshallah, I answer you. But not Khalid's lectures that he taught this because I will really need to revise those and Mishwar, I revise them because I don't have time. My email, chat. The one thing I want from your BLC, whoever he or she is, I want them to please, please, please try to convince Dr. Peter or Hassan. Oh my God, who did I send it to? I want to convince Dr. Peter or Dr. Hassan to allow you guys calculators in the exam because that will save you a good 15 minutes. Okay? So thank you so much for listening to me. If you have any questions, I still have 5 minutes for you guys. Otherwise, I will get back to my own stuff. Please, feedback, very important for my own self-development, please. Thank you so much. And thank you, people of PAL, Ijaz, and Sarah, I believe. Thank you so much for spending so much time working on this. Honestly, I'm sure everyone appreciates you guys a lot. Any questions or do we end the meeting? Yellow host, who's the host? Your input. No problem, my pleasure.
I can end the meeting if everyone's all right with that.
Okay, great. سبحانك اللهم وبحمدك أشهد أن لا إله إلا أنت أستغفرك وأتوب إليك.
Thank you very much, Aaron.
Assalamu alaikum. Take care. Enjoy.